Well, hello there, person watching this video. I'm Kellen, and I'm going to explain to you my theory of most everything in physics. Saying a theory of everything is pretty stupid, but in this case, it's actually, for the physics, it's pretty much a theory of mostly everything. It's everything I could think of in this whole thing. And I'll start into it in just a second. It really comes from a very, very simple principle. Very simple principle. And everything follows from there. And so I'm going to go through all the math and everything, but I'm also going to explain all the concepts and so you can really get it. And I'm going to explain, just like everything from quantum gravity to quantum mechanics to entanglement and why it looks like, things are, entangled and there's really no action at a distance or whatever. And I'm also going to show and demystify what's going on with all the forces and why, why people or physicists have thought that they all unify at something and show that they've actually been the same thing all along. And I'm going to go through and show what's going on with that. And I'm going to go through things like cosmology, dark matter, dark energy, dark whatever, you name it, black holes, and go through turbulence, go through chaos, go through fluid dynamics, go through Lagrangians, go through mechanics, all thermodynamics, just the whole shebang, it might start off a little slow, but I need to establish some concepts and some equations and whatnot. You can just tune out or skip ahead or whatever. And at the end, I'll probably get more into the mathematics. But I'm just gonna try and go along and go ahead because honestly, if you're a mathematician or a physicist, which probably those are the people that should be watching this video, but if you're one of those people, you should be able to do all the math yourself and take it and check it and do whatever and and buck up and do a little math for yourself. But I'm going to explain all the concepts anyway, so you're not going to really need to do all that. But there'll probably be quite a bit of math barf up on the board for you. So just a fair warning. Anyway, oh, by the way, I'm not just a floating stick here. I'm actually a real person, so hi there. Anyway, yeah, this whiteboard not doing too well, but I'm working with what I got, so yeah, video quality's amazing, isn't it? All right, let's go. All right, starting at the very beginning, the basic law of physics. I guess you could say this is new, or my law, or whatever, but anyway, this is the thing that lets you solve all the rest of the problems. And it's really fundamental and intuitive. It should make sense. But let's go through it. So this v is the regular velocity that you know. Really what it is it's the radial velocity. So velocity moving outwards from you. This is the curved velocity. You put a little squiggly above it, curved, curvy, whatever. You get the idea. This is the velocity along a curved path. So this would be the velocity outwards, a radial velocity. This would be the arc velocity, so the velocity along an arc path. And they add up to a constant, which is conserved. And this also happens to be the speed of light. And we shouldn't really call it the speed of light, it's actually just the speed of space. So we'll get to that in a little bit, but again, it's just the total motion is conserved. And that just means if you slow down in one direction, your motion's going to increase in another direction. So that's all this really is. And we can see other forms of it. This is, again, the same v squared. This curved v is actually just the radius times the angular velocity. And you don't need to know all this, but I'm just showing it to you. So if you're familiar with it, you'll go, oh, that's what that is. Anyway, this is r omega. This is the radius angular velocity. So this is the same thing. We can write this in calculus, fancy calculus notation with differentials. This is the rate of change of the radius with respect to time, blah, blah, blah. Rate of change with the angle with respect to time, angular velocity. And this is the total space derivative, or arc length. And people always write it as s for some reason. I guess for space, whatever. But we can also put it in differential form, like this. Or we can divide through by c squared, put it like this. Or move this thing on the wrong side of the equation, really. But this gives us the thing from special relativity, from Einstein's special relativity. And we notice that this is dr squared, when in special relativity it's ds. But we know we can see here clearly that that's wrong. And Einstein realized that was wrong too. That's why he developed general relativity to try and account for this error. But he didn't quite get it right because it's not really that space-time is curved. All it is that your path through space has some curvature. That's all that is. And this is supposed to be dr squared, not ds squared, like in this metric for special relativity. And this d tau, this thing that's keeping track of the time of the observed person or target, it's really this. And we can see why that's time. We can see what time really is. Well, a clock, it just spins around, and that's how it measures time. Well, if whatever you're looking at, if its path is spinning around, that's a measure of time. That's all time is, and we'll use that, and we'll explore that a little more. But that's it. It's not, I mean, you can throw time into a fourth dimension, and it comes in with a minus sign in relativity, and it gets all complicated. And then you can say, well, it's space-time now, and mathematically it has a curvature, and blah, blah, blah. But you're just making it harder on yourself. Really, space isn't curved at all. What's curved is your path. Maybe if you're only going outwards, then you have no curved path. And also, you end up having no mass, and we'll get to that. So this is vector form, if you want to, if that floats your boat. This is the total velocity vector, so again, the magnitude of it, or the length, is conserved, c squared. And we can see the dot product, cross product, blah, blah, blah. We can write, the radius. This is just Pythagorean theorem in 3 dimensions, three spatial dimensions, x, y, z, and put this in vector form. And we can see that in this special case, this unit vector in the radial direction is the same as, this is called the gradient, fancy thing. But we can put these in other forms and see, okay, that's what that is. So we can use that later if we want to get into using vectors and this and that. But that's the basics of it. This is all the same thing. These are all just different ways to write the same thing. Well, except for this is just defining what vectors are. But it's all the same thing. And we'll use this and we'll put it in a much simpler notation. But a lot of times people just make things harder than they have to be. And you can make it as hard as you want, but it doesn't have to be. So, anyways, let's move on. Okay, I'm just going to establish a few variables and whatnot for you. Again, of course, starting from the basics, the basic law of physics from which we can figure out everything. Well, conservation of motion. So we work it out and we see, oh, this is just the same as a unit circle. We can use sines and cosines, so good old trigonometry. And we can choose this one to be the sine. And we'll see that that's the right choice to do that, because when this theta, this angle, is 0, we want the radius or the distance to be 0. And so we can, if you're so inclined, you can do calculus on that and see that this really is the derivative of this. So, cool. And remember that the d tau thing that we were talking about, the proper time, or the time experienced by the thing you're looking at, is this. And we can work that out, do the integral, and we get that it's this plus this constant. And we'll figure out what this is in a second. But anyways, moving on, we can do a little bit of algebra, use a trig identity, etc., etc. And we see this is what people in relativity, in that cool kids club, like to call the Lorentz factor, or the time dilation factor. And we see why it's a time dilation, or why they call it that, because it's measured this tau thing, this d tau dt. The relative rates at which time's changing between the target and the observer. But what people missed, and what is really, really crucial, is that this can be plus or minus. This can be plus or minus. Usually they just fly by the seat of their pants, taking square roots all over the place, and forget that this can be minus. And they forget, or well, they just don't know in the first place that this is really 1 over the sine of theta. And this makes a huge, huge difference because this really explains what goes on with things like antimatter. And we're going to get to that. So we can just put this as 1 over sine theta. Sometimes written gamma. And it's useful to have this around because we can just multiply things by this and kind of remove their time dependence or correct for time. So it's kind of a useful tool. And we can also write this in the form of alpha, which is, it's all the same thing really, but in this form, it's between 0 and 1. Oh, that's interesting. That's like a probability. And, oh, that's interesting. It's a measure of the rates of the time between the two things, between the target and the observer. And we're going to see in quantum mechanics that that really is a probability, and we can use that. And we're also going to see that that's a coupling constant, what people call a coupling constant. It's not a constant, of course. I'm going to see that with a lot of things. It's not a constant. But this is like a electric constant, or electric factor, whatever. We'll use this, and we'll use this to great extent. Anyway, this is a kind of a list of things that change with time. So the theta is a function of time, the velocity is a function of time, etc., etc. All these, are about the same thing. Things which don't change in time, well, the only thing is this omega. And the other thing that we're going to define right now is the energy. Energy is just something which doesn't change with time. If you measure it, if you're the observer and you measure the energy at one point, then you measure the energy at another point, it's going to be the same. That's just what energy is. And, well, you can choose whatever units you want to measure it in, like inches. We measure length in inches and feet or meters or whatever, or we can measure things in gallons or whatever. It's completely arbitrary. There's nothing magical about it. This is just what people choose to measure things in. This is called the reduced Planck's constant, or h bar. But people think that this is a fundamental thing, but we're going to see in quantum mechanics that it's really not. It's completely arbitrary. So this is just a pure constant, just a pure number, with the units factor, whatever. Same thing with this c, or the speed of light. There's really nothing magical about it. All this is, well, from the point of view of the observer, the observer, their radius isn't growing. I guess if you're eating a ton, I guess it's going to grow slowly, but this is going to be 0. And so that means that this is 1. Okay, what does that mean? Well, if your radius is, I guess people's radius is about 1 meter, that's 1. Then c is about, 0.3 billion meters per second. Well, that means this omega is going to be pretty freaking big. So does that mean that you're a spinning top going around that fast? No, but what it does mean is that all of your parts, all put together, all of their omegas, their angular velocities, all put together adds up to this. And that's all this really is. That's why we measure this at the speed of light. So the amount of kind of angular motion or rotational motion in all of your particles is this. And that's the only reason we measure this as c, as whatever it is, the 0.3 billion meters per second. So there's nothing magical about this. It's just like saying, oh, why is an inch long? That's so amazing. It's like, no, we just defined it to be an inch. There's nothing crazy about that. Same thing with this. Although people misunderstand that it's fundamental somehow, that's really not, and we're going to see exactly how. So that's that. We're going to move right along. All right, again, energy is just a measure of this omega, this angular velocity. And we're just choosing to measure it in these type of units called h bar. And again, that's just arbitrary, and people misunderstand in quantum mechanics that this is somehow magical and blah, blah, blah. It's really not, and we're going to see that in a little bit. But we can use this, go through, this is omega, again, angular velocity. We say, oh, okay, well, what is theta? Well, theta is omega times t plus some initial angle. So if we say we're going to start our observation now, time is 0, and then, well, this is what the angle is going to start out at. So it can start out at anything. So you can say, well, we want to use energy. We're more comfortable with that. Cool. Multiply everything by h bar. Oh, that's interesting. What is this now? Well, this is now in units of what's called angular momentum, and that is the spin, or as people like to call it, the intrinsic angular momentum. It's really just the spin. That's what the spin is, and we'll see that. And so we can put it in this form, a little easier to remember, ethos, whatever. It's just a relation between the energy, time, Planck's constant, the angle, or the phase angle, is what people call it in quantum mechanics, and the spin. So that's it. We can use that too. Again, this is what the spin is. And we say, okay, well, what's time? Give me an equation for time in terms of all sorts of other things. Okay, cool. Well, what's this angle? Remember that the radial velocity divided by the speed of light is this cosine theta. So we can just take cosine inverse to get theta. Say, whoa, what's going on here with this crazy inverse trig function? And yeah, it is kind of crazy. We'll see that it causes a lot of problems later. But this is mathematically well defined because the velocity, the magnitude of the velocity, is never bigger than the speed of light. So this is a well-defined thing. So anyway, we can write out what time is in terms of this. And we're going to see that this inverse trig function is actually the culprit in a lot of complicated equations and a lot of what people aren't understanding, both about the physics and the math. We're going to demystify this when we solve the Riemann hypothesis at the end. So you don't have to believe me, but watch and see. Anyway, we can express tau in terms of other things very similarly and say, well, okay, when tau is 0, the time according to the person being observed and the time according to the observer, we say, well, let's match those at the start of our observation. Okay, we can do that with no loss of generality. So then we can figure out this little constant over here, blah, 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 figure that out, put this in terms of velocity now, and we can write down these kind of symmetrical looking equations for time. Time from the observer's point of view and time from the actual target's point of view. And we see that there's this kind of crazy looking inverse cosine thing. And we're actually going to explore that much later. But the math gets a little more complicated, so I'll save that for the end. Anyway, moving right along. Again, at the start of observation, time is 0, so t equals 0. That means we just have this phase angle being this initial angle. This is really just the spin apart from this constant factor. So what does that mean? Well, what if the velocity is 0? What if it's not moving? It's at rest. It's something at rest that we can look at and see, there it is. That's a particle. Well, then the cosine is 0, and the sign can be plus or minus 1. Remember, this can be plus or minus 1. People doing relativity forget that because they don't realize that this is plus or minus 1. It's really important. And what does that mean? Well, if this is 1, if the sign is 1, we're going to have a positive 1/2 with a factor of pi. So spin plus 1/2, really. If it's minus 1, we're going to have spin minus 1/2. Oh, that's interesting. What does this mean? Is this, what's going on here? Well, remember this sine theta is a measure of the rate of change between the observer's time, or the kind of the difference between the rates of the target's time and the observer's time. So kind of how their time matches up. And what this means is that if you're this guy right here, your time is going exactly according to the observer's time at the same rate. But if you're this guy, that means your time is going exactly opposite to the observer. Huh, that sounds kind of crazy. The time going in reverse? How can that happen? Well, it's very simple. You can wind a clock backwards, or you can play a movie in reverse. There's nothing fancy about that. It's just if you're that person, that's how things are going to look to you, and it's just a measure of you're matching, you're phasing, how things are matched up, your relative time. And so what happens is, well, people think this is matter, and people think this is antimatter. Like particle physicists actually write antimatter as particles with an arrow going backwards in time, and just think, well, it's not really doing that, but writing it this way works. No, it really is something going in reverse time. And this is also why people think, oh, why is there only matter in the universe? We don't see any antimatter. No, you do. It's all over the place. Half of everything is antimatter. It's right here. But people get confused in quantum mechanics because they think, oh, well, these are both electrons. And yeah, you can call them electrons. You say, well, it looks like they either, if it's like this, it can't occupy the same state. And if it's like this, it can pair up into, whatever, and occupy the same state. No, if it's doing this, it's actually turning into light. And if it's, and we'll see exactly what that means in a second, but if you put these things together, then if you put this together with this, it's going to give you spin 0. If you put this together with another one of this, it's going to give you spin 1 down here. And that's, you can combine these things and pull them apart to your heart's content. And that's what people interpret as particles and antiparticles annihilating and antimatter and matter. It's all the same thing. It's really not that complicated. It can be more complicated if you make it, but it doesn't have to be. Now, moving on. What if, instead of being completely at rest, it is going at the actual maximum radial velocity outwards? So it's going away from you as fast as it can, or towards you as fast as it can. Well, the cosine is going to be plus or minus 1, the sine is going to be 0. Okay, what happens if the cosine is plus 1? Well, you're going to get the spin 0 or spin 2. This, again, this dot, dot, dot just means, well, if you're at 12 o'clock and you go around the clock at one time, then you're going to come back to the same point. So it's equivalent. And that's all this dot, dot, dot means. And I just wrote this out. Again, this is the same thing. This works out to the same thing, and you can keep going in plus or minus direction. But with the 0 here, people interpret this as a Higgs boson, and people interpret this as a graviton. It's the same thing, and it's really just light. It's a photon. It's light. That's all it is. This Higgs boson mystery and this graviton mystery, that's all it is. And people think that it's a different thing because, well, we'll see exactly why. The Lagrangians are wrong, and their equations of motion are wrong, and they have all these holes in their math, and they're thinking that these are all separate particles. They're really not. It's just light. And, well, if it's minus 1, then it's just, we would see that as spin 1, which people typically call a photon. They're both photons. It's the same thing. What it means is one is moving away from you, and one's moving towards you. Oh, that's interesting. What does that mean? These? Huh. So this would be positive velocity moving away. What does that mean? Well, if something breaks up into pieces and part of it flies away from you by conservation of motion, remember, the other part of it moves towards you. And that's going to look like an attractive force. That's why people think that the Higgs boson gives things mass, which gravitates, and that's why people think that the gravitons cause gravitation. It's because if it emits a photon like this away, then the object, by conservation of motion, moves towards you, and it looks like looks like a force. It looks like a gravitating thing. But if it's this, if it emits a photon or light towards you, then the rest of it has to move away. And that is going to look like repulsion, or for example, like charges repelling. That's what this looks like. So this is going to look like an attractive force, and this is going to look like a repulsive force. But it's the same thing. It's light. There's really no particles and antiparticles. It's the same thing. It's the same exact thing. It's not that complicated. If you want to make it complicated, you certainly can, but you don't have to. So we're going to use that and keep going with it. All right. All right, what is mass? Well, things that are more massive are harder to move. And we only measure mass when things are still, when they're stopped. So when they're at rest, when v equals 0. So at this radial velocity equals 0, it's just going to be some constant times this energy. So that makes sense. Well, at any fixed distance or radius, this omega is going to get increased as the velocity goes down. Same thing with the mass. So we know if the velocity goes all the way up to the speed of light, positive or negative speed of light, then this mass should go to 0. So we know we need to throw in a sine theta there, because the v is determined by the cosine theta, so the m will be determined by the sine theta. And just by looking at the units, by dimensional analysis, what's the fancy term for it? Just looking at the units, we can tell that this should be h bar over c squared. Just looking at the units for mass. So nothing fancy going on there. It's just making the units match. So we can put this on this side, rewrite it a little bit to E equals mc squared gamma. And if it's at rest, then this gamma is, which is 1 over the sine theta. The sine theta is just 1, so this gamma would be 1. And if it's at rest, then we get E equals mc squared, like the good old equation that everybody writes down to sound smart. But what it really is this E equals mc squared gamma. And this is what Einstein actually wrote down. But still, that wasn't quite right, because gamma is supposed to be positive or negative, because it's secretly 1 over the sine theta, which can be positive or negative. And you may say, well, wait, that's kind of crazy. That means mass and energy can be positive and negative and all that stuff going on? Well, it's not really that crazy. It's actually pretty simple. The mass, if you take the mass to always be positive, then sometimes the energy can be positive, sometimes it's negative. In the case of negative, what happens is, for example, in quantum mechanics, with trying to explain antimatter, people said, well, maybe it's just this, you've got this negative energy C, and like maybe there's holes in the sea and stuff, and we don't know, but maybe it's like that, and it really didn't make sense. But this is the explanation for that. It's actually that this can be positive or negative, and you need to account for that. And there's really no antimatter, it's just matter. It's just things with their timing going in different directions. And again, things having their timing going in opposite directions is not really that crazy or complicated or out there. It's like you're driving a car, and if your wheels are spinning this way, you're going to go that way. If your wheels are spinning that way, you're going to go that way. It's not that complicated. So anyways, we can just work this out a little bit, put it in a different form. It's all the same thing, but this is just a different form we can use. Moving on to momentum. Why use a letter P? I don't know. People have always used P for momentum, so I guess I'll stick with it. Anyway, we know it depends on mass and velocity, but we know that at rest, at rest, we have a mass, but if we're moving at the speed of light, then we're also supposed to have some momentum. So we need to multiply by this gamma, and that just gets rid of that time dependence, like we were talking about earlier. You just multiply by gamma, and then suddenly this is good to go. So we work that out. See that this is what the momentum is in terms of energy and cosine, and we can put the momentum and the mass together in the same equation, and we get this, and we work it out. We see it's secretly just the trig identity, a unit circle. And we can write it in another form, this form, which you might recognize from special relativity. And we can then just divide through by E, by the energy. So we just get a regular expression for the energy, and we get, it's got mv squared gamma plus mc squared over gamma. Oh, that's interesting. That is the kinetic energy term, and that's the potential energy term. And you might say, wait, from physics class or whatever, I never took physics, but they seem to tell you, well, this is 1/2 mv squared. Well, no. It's the total kinetic energy is mv squared. If you put 1/2, then you're only looking at the energy of 1/2 of the system. Or if it's 2 particles, you're only looking at the energy of 1 particle. Or if the observer is supposed to be counted as one of the particles, then you're only looking at the target or the object, the other object, and that would give you a 1/2, and that's not correct. The total energy is this, and this is the potential energy here. So people, for some reason, write this as a big capital T. I put an E there just so you know it's energy, and they put the potential as the big capital V for some reason. It's nice and confusing. Anyway, that's the kinetic energy is this. The potential energy is this. And remember that this is what the distance is, or the radius. And we can multiply mass times radius and get this expression. And just work it out. This is just kind of a conversion factor. Looks like charm, like that stupid name for that quark. That one particle that people are talking about. We'll get into that and what that's all about. But this is just an easy way to remember the conversion factor. And this is over the quantity Rm, whatever. It's just a handy tool to convert. So we can use that on the potential energy, put it in this form. Oh, this m squared c cubed over h bar thing. Well, we know that the potential energy, well, it's really minus the work. But the work is just force times distance. That's all that is. Or you can figure out the minus sign to your heart's content. But this is the way that the potential energy is usually written, minus the force times distance. So when you take the partial derivative and everything, you get this. But we'll actually examine this and see what's really going on. And we notice that, oh, hey, this is the form that force is in. Well, this is one of the forms that force can come in. We can rewrite this in all sorts of different ways. And it'll look like totally different things. But there's really just one force. So there you go, Star Wars fans. But really, there's not even a thing called force. All it is a measure of acceleration, or it's saying, well, one thing is moving slower or faster relative to another, and that's going to look like a force. So that would make Newton relieved from the dude from a couple hundred years ago or whatever, whenever he lived, who was worried about gravitation being an action at a distance and didn't really know what that was all about. It's not really. It's just one thing moving more slowly or more quickly relative to another. And why would it do that? Conservation of motion. If it's gonna if it's gonna move more slowly in a radial direction, then its motion is going to go into rotational motion. So again, that's just one way to write the force. We can use all sorts of conversion factors, and we can. There's more ways to write force than you can shake a stick at. Well, I'll shake a stick at it. But this m squared times this constant. Well, when particle physicists were looking at things, in particular nuclear interactions and things, they recognized this was in there somewhere. This m squared times a constant. And so then they figured, well, the potential energy would have would be multiplied by this distance, and so the potential energy would just grow linearly with the distance. That's like a law for a spring, or a string. And so that's why they came up with string theory, is because they saw this pattern happening in particle interactions. But they didn't really understand this. They didn't really know what was going on. So to try and make things work, they, try to say, well, the renormalization, you need to add extra dimensions. It's the only way to get it to work. And the renormalization deals with the Riemann zeta function and the Riemann hypothesis and whatever. And people didn't really understand that until this video, I guess. But this is really what's going on. So string theory was, they noticed something, and they were kind of on the right track, but they went way off base. They made a lot of cool mathematics and whatever. And, I mean, it's a cool theory, interesting, whatever. But that's the deal. So we're going to take a look at that in a little more detail. All right, now we're going to explore force some more. All right, well, first of all, what's acceleration? Acceleration is it's the derivative of the velocity. It's how the velocity changes with time. So if you're slowing down or speeding up, that's acceleration. And so we know how to do that. That's just this expression. We can just rewrite this a little bit in terms of mass, and there we go. We get that expression for mass. And we see, oh, ma, that's this thing that we figured out was the force before. It really is the force, just like, just like you've always been told from the good old days, F equals ma. So, and again, this is the form, the way it's written is the form that string theorists recognized, and so it's kind of like a string force. It's what this also is if you don't have the equations of motion correct, like if your Lagrangian is off, then you're going to have terms like this appearing in here with other little kind of constant factors in here. And it's going to look like a scalar field, or it's going to look like a Higgs field, and it's going to look like there's supposed to be Higgs bosons. But remember, the Higgs boson it's just light. It's just a photon. And just like a graviton, it's the same thing. So that's why this term will appear in there, and that's why people will look for these Higgs bosons and be like, oh, I found one. But the thing is, the Lagrangians and the theories and the math that they're working with has tons of holes in it. So there's going to be a Higgs boson for every hole that you need to fill, and that's exactly what happens when you get into like supersymmetry, for example, when you try and correct these so-called fine-tuning problems and this and that with the standard model. You get all these correction terms, and you get more Higgs bosons, and you can just keep going. You can keep going and keep going. It's kind of like trying to calculate or write out the numbers or the digits for pi. I mean, you can just keep on going. You can go and go and go, and people will be like, oh, I found a new digit for pi. It's like, good for you. Pi is real simple. It's just the ratio of the circumference of a circle to the diameter. There's nothing too complicated about that. And if you know that, then you can make all sorts of formulas to calculate the digits of pi if you really want to. You can write computer programs that'll do it. So, but if you just stared at a random chunk of the digits of pi, you probably wouldn't be able to make much sense of it. Just like particle physicists looking at all these different particles that they think are different particles, and looking, oh, there's a Higgs boson, there must be a Higgs field. No. It's this. It's just force. And you can write it in tons of different ways. And so we're going to do that. All right. Well, using this nifty conversion factor, we can write it in this form. We see that this is that arc velocity, the velocity traveling along the outside of a circle or whatever. It's not the radial velocity, it's the arc velocity. And this is centrifugal force. that's what this is. It's the velocity. That's why I wrote the v with a squiggle, because it's still velocity, but it's the velocity along the arc. And that's centrifugal force right there. All right, well, let's take a look at what this really means. How about density, or mass density, if what people call it. People usually write it as rho for some reason. Looks like a P, but I'll try and make it look different. But anyway, the density is just mass per volume. Volume is just distance cubed, and we can work out what that is. Put that in this form. And, oh, that's interesting. What's this capital R that you're using, Kellen? Well, it's just this. It's the regular distance times the gamma. So it just corrects or gets rid of the time dependence. So what that means is that this big R is just a constant with respect to time. It's just in terms of the energy. That's all, just in terms of the energy. So it's a constant. It doesn't vary with time. So we can write the density in this form. The density, this part, energy doesn't vary with time. This doesn't vary with time because it's just a representation of the energy. So this is constant. This is 1 over the arc velocity squared. So if the density is constant, then this arc velocity is constant. So if the density is constant, then the rate at which you're moving around, your velocity along the arc, is constant. And guess what, guys? That's why people think there's dark matter. Astronomers look out into space and they look at galaxies and they say, oh, well, most of the galaxy, except for the center, is about the same brightness. So we're going to say it should be about the same density. It should have about the same mass density, pretty much uniform. But what's going on is that this arc velocity, they just think it's normal velocity. They don't make the distinction between arc velocity and radial velocity. It's really important to do that. They see that this arc velocity is constant, is pretty much constant, where they say that the density is pretty much constant. And that doesn't jive with the regular, either the Newtonian way to do gravity or the Einsteinian way to do gravity. The general relativity, neither of them work. And so people assume that general relativity is correct and everything, and they say, well, that doesn't match up. There must be dark matter. There must be extra matter that for some reason we can't see or interact with or do anything, but it's got to be there because it's gravitating. No. The math, the equations are wrong that you're trying to use. It's really just this. It's this simple. It's this dark matter effect. And that's it. I mean, it's just the centrifugal force, really. So I guess this is like the dark side of the force or something. I don't know. That's a stretch. But they don't know the power of the... Yeah, I'll just leave it. They don't know... Fine, I'll say it. They don't know the power of the dark side of centrifugal force. Anyway, well, what is gravity? How do we actually represent it? Well, we use this and just use the conversion factor. Or, well, we don't actually use the conversion factor. We just put an r squared in the bottom. And we have to put an r squared up here. Oh, well, we know that people usually write the gravity in this form. Well, that means that this is not really a constant. This supposed gravitational constant, not a constant. Not a constant at all. What is it? It's this. It's this right here. And it works out to this. So we can put it in this form. And we can throw the energy on this side with a 1 over speed of light on there. And this is the form of the Einstein field equations. Just recognize this. You can, in the privacy of your own home, convert this into tensor form. I'll write the tensor form for you in a bit. But this would be the energy momentum tensor over here. This would be G, the supposed gravitational constant. And this thing over here, this would be the cosmological constant, which is not a constant either. And this would be the thing that people think is dark energy. Like, oh, well, it's this mysterious cosmological constant, this force thing that grows with distance and blah, blah, blah. Nope. It's just that the equations for gravity, general relativity, is wrong because it's only an approximation. It's only an approximation. This g is not constant. So if you try and act like it's constant, then you're going to have a correction term. And so you're going to have another term over in here, which is going to have an energy in front of it. And guess what? This energy is just h bar omega. The energy is simply a measure of the curvature of your path through space. So what ends up happening is if you put it in tensor form, you get a curvature part, and you get a curvature tensor. And so you can go through the whole formulation of putting it in tensors and include time as an extra dimension, and say this new object, this new four-dimensional object called space-time has this curvature. I mean, you can say all that, but all you're really saying is you need to add an extra factor of this energy because you're going with the wrong equation. This g is not constant. So there you go. That's this effect of dark energy and the dark matter and dark whatever. It's really not that complicated. So next we'll take a look at the expansion of the universe and Big Bang and wrap that up. All right. All right, now for cosmology. Well, again, motion is this. You've got radial velocity, and this is the arc velocity. We can put that in terms of distance and angular velocity. So we can put that in terms of energy, and lo and behold, if energy is zero, if there's no energy, then velocity, the radial velocity is, well, the square of it is c squared. So the radial velocity can be plus or minus c. What does that mean? That means empty space, whatever we would call nothing, moves away from us in all directions at the speed of light. So it's really just the speed of space. It's empty space. That is the expansion of the universe. Why does it look like the universe is expanding again? Well, because empty space moves this speed, but everything else, if it has, mass or energy or whatever, it's going to move in a curved path. That's what that is. It's a curved path. So if you're not moving radially outwards at the speed of light, then, well, you're not moving as fast as the rest of space. And so that's going to look like an expansion of the universe. And say, well, what about light? What about photons? That has energy. Yeah, it has energy. That's why you can make light bend, because it's got energy. It's got this curvature in here, this angular velocity. That's the reason that light can bend. But space itself, just empty space, is not curved. It's just there. It's just space. I mean, we can call it nothing or we can call it something. It's really just point of view. You really just whatever you want to call it. It's like someone saying, well, what's up versus down? Well, if you're on this side of the planet, if you're standing up on the top of the planet, where we are at the top, I'm saying, then that would be up, that would be down. But if you're on the other side of the planet, it would be completely the opposite. But, it's relative. But you wouldn't say like, oh, well, if someone's standing next to you, you wouldn't say, well, wait, what's up for me and down for you? It's like, no, it's the same thing. But it's still just relative. It's all point of view. So that's really all this is something versus nothing. And we can see how we can get something from nothing. If we have something to call nothing, then we can easily do things like this. +1 and -1 at the same time. There you go. And we can do it again. Oh, now we have these three particles. If we were thinking in terms of particles, we would say, oh, we have these particles and an antiparticle and blah blah blah. No, it's just this. It's just well, the sum of them. This motion is conserved for your point of view. And moving on, what does this mean for distance and so forth? Well, this is what distance is, remember? And remember, this is what the sine theta is. It's the rate, it's the time rate of change, the rate of change with which the object's time changes with respect to the observer's time. Now, if that's fixed, that doesn't change. If we set it and say this is what it is, well, if the distance goes down to 0, then that means this would be 0. And that means the energy becomes infinite, plus or minus infinity, actually. This denominator is, if that's positive or negative infinity, then it's going to make this whole thing 0. So what that's really saying is that in a single point of space, an infinitesimally small point of space, or a small zero area or zero volume, there's an infinite amount of energy in there. But you could say it's positive or negative. So in a way, you can say, well, I guess it kind of cancels out. But it's the same thing. It's that whether you look at it, it's positive or negative, and we'll see exactly how that works. Again, if the distance goes to infinity in either direction, positive or negative, then the energy goes to 0. What does that mean? That means infinitely far away, there's still empty space. So empty space goes on for all directions, and again, space moves at the speed of light. It's the speed of space. That's all it is. Now, what happens if the time between the target, or the object, and the observer is the same? What if it's synced up? If it's 1? Well, if there's positive distance, if we're measuring out distance to something, well, then if we try and shrink down that distance, then as we do that, this energy that we measure is going to go to positive infinity. So from our point of view, if we say, oh, okay, well, whatever we're looking at, let's try and look at, any point in the universe, or let's try and look back to the Big Bang or something. Well, if the point we're looking at, if our time matches up, if we see something with probability 1, and it's the same time and everything, and we're measuring distance positive, we're looking at it, then as we try and shrink down this distance, as we're trying to look back in time and say, well, what happens if we go back and try and shrink down this distance? Well, energy's going to go to positive infinity. So from our point of view, if you trace everything back, you can trace it all the way back to a single point of nothing, not just a compact point, but a single point of actually nothing. That has positive energy from our point of view. If it had negative energy, well, then our time would be reversed relative to whatever we're looking at, to the rest of the universe, and we don't see that. So the only way for us to experience time is in forward time for our point of view. So to our point of view, when you trace it back to the big, quote, Big Bang, it traces back to a single point with infinite amount of energy. And not just a compact point that was just sitting there for some reason, just hanging out, like, well, I wonder when I'm going to bang. No, all the way back to nothingness, really. And, I mean, that's just something and nothing. That's really a relative term. It doesn't really make much sense to say something versus nothing. I mean, it's like this. Well, you say this is nothing, this is 0. Like, well, you wrote down a 0 on the board. I mean, or I did. I used a marker and drew it. I mean, so that's something. But then, so you have to have something to represent nothing, but at the same time, nothing to represent something. So it's the same thing. It's like up and down. Same thing. Can't have one without the other. So moving on. Einstein field equations. I told you I'd write out the tensor form. This is it. This is the Einstein tensor. I put a fancy, I kind of tried to make it block lettering to make it look different. These are tensor indices. This is the cosmological constant term. This is the space-time metric. This is this 8 pi factor because people are usually trying to deal with spherical things or volumes and use 8 pi's and whatnot. This is G. Now remember, this G is not actually constant, and there are a lot of problems with trying to keep it, with trying to say that it's constant and trying to solve things from there. So it's not really constant. But in Einstein's equations, this is just Newton's gravitational constant. And this is the space-time, or the energy momentum tensor. So it's just really energy, representation of energy. So this is what it is. It looks pretty complicated, but one possible solution to it is the Schwarzschild solution, and it's this. It looks like this complicated thing, and what we see is, well, we have these terms in here that, well, it has the G, has M, and R. Well, normally, people think that this G is constant. Well, if this G is constant, if it's really a constant, then there's some ratio between this mass and this radius where this whole term will become 1. And then you'll have 1 minus 1, which would be 0. And that would be called a horizon, or an event horizon. And in this case, you would say that the space-like coordinates and time-like coordinates will switch if this swaps. And then also if the r is 0, if you shrink down the radius to 0, then if g is really a constant and you shrink down this r to 0, that would be a singularity. And this is where people got the idea of black holes. They looked at this equation, or this solution to Einstein's general relativity equations, and said, well, what does this mean? What are the consequences of this? Oh, look, it means there's an event horizon here, and it means that it's going to be a black hole, and it's going to suck everything in. And then down at the actual point, when distance goes to 0, that's going to be a singularity. And so this is where the idea of black holes got started. And we can see, well, we can work it out and see what actually happens, because this, and see if this solution is actually correct. If this is the real deal, then we can work it out. But I want to say, I mean, black holes, the idea is cool and all that, and, like science fiction sometimes. But, we gotta look at what's in front of us. No wishful thinking. The idea of Santa Claus is nice and all, but if you want to get your kids presents, you got to get them yourself, or have your grandparents do it or something. But anyway, this, we can work it out, and we see the consequences of what happens. It ends up going to this alpha, this sine squared theta equals 1/2. But wait a second. For light, the velocity is supposed to be plus or minus c. That means the cosine is plus or minus 1. That means the sine is 0. Well, wait a second. 0 does not equal 1/2. So this doesn't happen. There is no event horizon. There is no singularity. Sorry to say it, but there are no black holes. Now, why do people think there are black holes? Because nobody's ever observed a black hole. No astronomer has observed a black hole. All they see is a region of cluster of stuff, stars. It's really bright around it, and they say, well, that has so much mass. We can tell by all sorts of factors and this and that it should have so much mass by using general relativity. And because it has that much mass, according to general relativity, it should have a black hole in there if it's big enough in a small enough volume. But what the reality is that this G is not a constant. And that changes everything. That changes the whole thing, the whole kit and caboodle. So the upshot is that there are no black holes, and that's why people don't see them. And I mean, and it makes sense because there are a lot of problems in cosmology that people are trying to wrestle with and say, well, wait, did galaxies form and then they collapsed into supermassive black holes which anchored the galaxies? Or were there primordial black holes that existed at the Big Bang and then galaxies formed around those? And, you know, people are arguing and don't really know. And the thing is, there are no black holes. It's the fact that this equation, the Einstein field equations, is not quite right because this G is not a constant. Newton's constant is not a constant. So there are no black holes. And just from an intuitive standpoint, we know that there can't be black holes because otherwise there's plenty of energy going around. I mean, we would expect to see little black holes popping up here and there. But then people like Stephen Hawking came across and said, well, maybe they radiate away things, they have entropy and this and that, and so they can evaporate or whatever. And that's kind of on the right track because, yeah, they should evaporate because we don't see them. I mean, otherwise, you know, good luck on your drive home, not suddenly turning into a black hole. They're on the right track because they can't do that. And it turns out there are no black holes. It's just a mistake of interpreting this equation incorrectly, the fact that this is not a constant. And, I mean, if you really want to think of, say, something's more like a black hole or a white hole, I mean, everything is like a black hole or a white hole. Everything can emit light or absorb light. I mean, this part of the black ink is like a black hole. It's absorbing light, I guess you could say. Or this white part of the board is like a white hole because it's emitting light. But everything can do that. I mean, we saw that earlier with the whole thing about the question with the Higgs bosons and the gravitons and this and that. It's just light. And people are making it a lot more complicated than it has to be. But that's it. So we're going to go along and I think get to entropy. I guess I'll do that next. All right. Well, before I get on to the next topic, I figure, I guess that whole thing's been about an hour. You're probably feeling like this. So we're about halfway through, so I'll just go ahead and review some of this stuff. Make sure it's sinking in or not, or give you a break to get a snack or whatever. So here we go. It all starts with the law of motion, or the basic law of physics. It's just, I mean, if you're a mathematician or whatever, I guess you could call that an axiom. Something that we just look at the rest of the world and say, huh, it looks like that's how things work. And then we can use this and derive all sorts of things in physics. And we did that over this last section, everything from special relativity to general relativity, derived the Einstein field equations and showed that the Einstein field equations are really just an approximation. So we derived all sorts of things, and we're going to continue doing that. So again, the law of motion means that if you slow down in one direction, you got to speed up in another direction. So if it looks like something's at rest, but it still has it still has energy, it's not just empty space. Well, it's going to have rotational motion in there, and that's what we interpret as mass. And you say, well, wait, you said something. It's going backwards in time if it's spinning the other way. Yeah, that's a relative thing. So why would parts of the universe not appear to be shrinking or growing? Well, some parts do appear to be shrinking. That's gravity. But the thing is, if the rest of space is going outwards and your path is curving either in this direction or in the opposite direction, either one, your motion is going into more rotational motion. So your motion outwards is reduced. And so that's just it's a very simple concept. That's just motion, and that's why people get confused with matter and antimatter and thinking there's a difference and all this different stuff. It's really just this. It's the same thing, and we call it matter. We call it matter when it's completely stopped. When it's stopped, it has no radial velocity. We call that matter, and we can figure it out by this equation here. Light is something where we say it has only radial velocity. It doesn't. It has no radius. We can't measure a distance on it or anything like that. We call that light, and we can. Or there's people that are misunderstanding things and don't really understand their Lagrangians or their or what's going on in the math that they're looking at. They think that there's differences between photons and Higgs bosons, and they try and think that maybe the Higgs boson has a mass when it's really just their equations are off, and we'll actually see that. I'll show you exactly why. But really, this is just an arbitrary distinction, light versus matter. I mean, you see this angle, this can go between anything. So these light and matter, I mean, it's changing between itself all the time, and we're going to see exactly how it changes. We're going to get into entropy and thermodynamics and chaos theory and all that, and really go through it and see what is actually happening. So that's what we're going to do with that. And we looked at force, and we saw that it's all the same thing. There's just many different ways to write it, and it makes sense that this is the same thing. I mean, you look at the law of gravity that people write down and the law of magnetism. I mean, it looks the same apart from a few numerical factors, and it's because it is the same thing. It's the exact same thing, but people are assuming that certain things are constant, and then they change and they say, well, this is supposed to be a constant, but we're not getting this theory breaks down, so, well, let's just make a new one. Let's, on our gravity breaks down, so let's call this new one electromagnetism. Oh, that breaks down. So let's call this one the weak nuclear force, and then the strong nuclear force. And, then on larger scales, it's like, oh, well, the theory of gravity is not working. Oh, this looks like it must be dark matter, or, then for the other side of it, the dark energy. So then people come up with things like quintessence. It's like we're just going back in time to the ancient Greeks where people thought everything was made out of like air, fire, water, and earth, and some mysterious ether. Or like people used to think that light just moved through this mysterious ether, and the light was waves through that. No, it's actually just space. I mean, I guess if you want to think about it, we can, when we tackle the Navier-Stokes equations, we can see that I guess we could think about space as like an incompressible fluid. But, I mean, that's all your point of view. I mean, we went over that just a little bit before. How if you try and think about collapsing space back down to a single point and saying that's the Big Bang, well, then it would have, you could say it has either positive or negative infinity of curvature. And it's a similar thing to trying to, mathematicians or topologists or whatever, when they make a cone. Well, the cone is, you can flatten it out all over the place, except for at the very tip of the cone. And then mathematically that would have an infinite amount of curvature just at that very tip of the cone. So it's about the same thing. It's kind of silly to talk about those things without understanding the real concept behind things. And that's what goes on a lot. It's when you don't understand the concept and you don't really know what you're looking at, it looks really, really confusing. And that's just like looking at a random chunk of the digits of pi. I mean, yeah, if someone came along and predicted the next one and said, this is the next digit, people would say, oh my gosh, that's so amazing. How did you do that? But it's not really that amazing. I'm sorry, it's not. Unfortunately, it's not that amazing if you really know the fundamental principles behind it. And so that's what I'm trying to, just let people know. I don't think I'm smarter than anyone. I've done plenty of stupid things in my life, believe me. So I am definitely not smarter than anyone. But, I think we're all roughly the same intelligence. So I'm just trying to get across things that I figured out to you. So anyway, that's that. And this is some useful math equations that we can use, and just throw at some problems and not have to think as much. So we just remember these. We can just plug these in and use them. So take a break if you feel like you're going to be squished underneath a huge block of information, or if you think it's wrong and you think that's not really there, then I guess you can turn the video off. But if you're curious, keep on watching and we'll continue with it. All right. All right. Well, using what we know, we can write down distance is this, momentum is this, and we can multiply them together. Things cancel, and we get this right here. Say, oh, that's interesting. What's going on? Well, we see this h bar here. This h bar, this reduced Planck's constant, is only here because we decided to measure energy in terms of measuring this omega. We put an h bar in front of it because we're like, well, we're comfortable measuring energy in terms of h bar omega. This h bar is just a constant. It's just like saying inches or feet or whatever. That's the only reason it's here. It's just sticking around because r wasn't measured in energy, but momentum was measured having to do with energy. So that's why that's in there. But you can see r still has this omega in it, and then momentum still has this omega in it. So this h is just arbitrary. There's nothing special about it at all. But what we do see is this sine, or the sine and the cosine. And so what's going on with that? Well, first of all, if we take a constant energy, constant omega, well, then for zero momentum, if it's at rest, if it's just sitting there, you can say it's not moving, then the cosine's 0. But this sine theta can be plus or minus 1. So that means if we know that the momentum is 0, just absolutely 0, then we are not going to know exactly what the position is. Not going to know exactly what the position is. And likewise, I mean, even if we said, well, maybe this omega can be 0, well, in that case, then you'd get a divide by 0 thing going on here, and so you'd still have problems. So anyway, that's what's going on here. And you can see it just from here, because if you put in, if momentum is 0, then that's going to be 0 on this side, and 0 on this side here. The cosine is going to be 0. So it's going to be 0 times 0. So you're not going to be able to get any information out of this regarding the distance. So that's what we call it the uncertainty principle. And likewise, if the distance is 0, then you get plus or minus on the cosine. So you don't know exactly what's going on with the momentum. And that's just a clear way to put it, right? Just like this. So what we can do is we say, okay, well, you notice there's a trig identity hiding in there. So multiply both sides by 2. And we work it out to this and say, oh, well, that's interesting. What happens when we shrink down the distance between these? Let's say we have two things and we're measuring them with momentum. What happens when we shrink down the distance to 0? Well, we know that this needs to be 1. And so this will shrink down to 0 also because it has this in it, has that factor in it. So this would shrink down to 0, and in this form, it's going to be 1. So this is the transition between what people would think of as a particle and an antiparticle coming together at distance 0 to produce a photon, which has this cosine theta as 1, meaning the velocity would be the speed of light. So these two things, these quote particle and antiparticle, come together, and in the parlance of particle physics would be annihilate to form a photon, which conserves the momentum of the original two things. And this is we can write the new momentum and distance in terms of a new phase angle like this. And again, this h bar just goes along for the ride simply because we're measuring it in units of h bar. That's all. And so this is another way to write it, the quote uncertainty principle. But the thing is, people don't realize that this sine 2 theta is sitting around. They don't realize it's there, and so they just see something like that and say, okay, whoa, that's crazy. That h bar must be fundamental somehow. Nope, it's not. It's just this. Just this right here. Okay, so what does this 2 theta mean? How can we deal with that? Well, if we want to find this 2 theta in terms of something that we know, we want to find the sine of 2 theta in terms of sine of theta, okay, well, we could just use a little trigonometry, plug it in here, square it. Okay, cosine squared is 1 minus sine squared, whatever. Well, we see, okay, well, let's call theta and this thing. Let's say it's 2 to the power of something. That way, when we go from theta up to 2 theta, when we generate another particle or combine two particles, when we change from one particle to two particles back and forth, vice versa, we want to quantify that somehow by this n. This n is counting that. So it's going to be, well, we want this theta naught, this initial theta value, to be in there. So if n is 0, we get back what we're used to getting, that theta at initial value is the initial value of theta. And this is, remember, the spin divided by that h bar, Planck's constant. That's all that is. And so we get this for the sequence, if we want to make a sequence out of this. And this is what we get. It's called the logistic map. You might recognize it from chaos theory. Logistic map at the logistic R parameter being equal to 4. But what happens here is this is what's called chaotic. And if this initial value of theta is pi times a rational number, then this sequence is periodic. It repeats, or it's predictable. Or, well, I mean, we can predict it anyway, but it's really hard to predict otherwise. This way, if theta naught is a rational number times pi, we can write this as in terms of the spin being a over b, where a and b are integers, then this will be a periodic sequence, something that's repeating, something that you could actually put into a computer in terms of ones and zeros. But wait a second, if you're dealing with the real number line, then the rational numbers are only, are not very dense compared to the irrational numbers, which really fill up the whole thing. There are infinitely more irrational numbers in any chunk of the real number line than rational numbers. So by and large, you're not going to be able to plug this into a computer and really calculate things. So, I mean, The Matrix is an awesome movie and everything, but realistically, we couldn't be living in a matrix. So, sorry, but that's what's going on. However, we can represent something sometimes to a certain degree of accuracy as binary digits. And if that's the case, then we'll see in calculations and things different binary related things, different information theory related things showing up. And this is the root of it all right here, this logistic function relation. And that's really because we're using a trig function. So it's all related, and we can write out what theta is. Remember, we had it in terms of time, and we can have it in terms of this n, this number that we're using to count transitions here, or count when we go from one particle to two particles or back and forth. And so we work this out. It's a logarithm base 2 of this thing. Now we can see that this n, this number, if we have a positive energy or fixed energy and spin, this is going to increase with time. That's why entropy increases with time, or it looks like it. This can be negative in certain cases if we're dealing, if we have other values in here, and that's why we get the laws of thermodynamics, which aren't really laws, but they're approximations to a certain extent, and this is really what's going on behind it. Another thing that we recognize is that we have this 1 plus e over s times t. Well, usually people think that this is supposed to be an exponential function in here, called the partition function. Well,
this looks like an exponential function if this part is really small. You can do some calculus on it and see for yourself that this will look like an exponential function when this amount here is really small. And so if people think that this is really an exponential function and they start doing calculations with it, they're going to come up with the wrong answer. For example, with the sun, around the sun, the corona of the sun, people are expecting it to be much, much cooler than they measure. And people don't know why, and it's just kind of like one of those problems, like, well, that's interesting. Maybe it has something to do with magnetism or some complicated magnetic reconnection, blah, blah, blah. No, it's this right here. And we're going to see how this plays into temperature and the connection and everything. But this is what's going on. It's because people don't know this is what's going on in here. This is not an exponential function. It looks like an exponential function when this gets small, especially at the start of your observation. If you say time is 0 and I'm going to start measuring now, then this is going to be 0 and it's going to look like an exponential in here. But this is what's going on. This is what's going on here. Now with entropy, we can say entropy is this number times a Boltzmann constant Kb. There's nothing special about this. All this is a conversion factor between the units that we're choosing to measure energy in and the units that people measure temperature in, like kelvins. So it's just a conversion factor. It's like saying inches versus centimeters, convert between them. There's nothing special about this. The real thing is this number that we're using to count. And we'll use that and see what actually happens in phase transitions between things, like going from gas to liquid and vice versa, and all sorts of things. So we saw that it's not only about phase transitions between liquids and solids, but it's the same thing happening between what we like to call matter and what we call light. It's the same thing going on, and this is what we can use to count that. All right, well, now I'm going to get into some quantum mechanics, just go over that and show you what's going on with that. All right, here we go. So, using what we learned about entropy, it's just this number. Entropy is really just this number times the Boltzmann constant. But we can just deal with this. So, we can rewrite this, do a little algebra, and put energy in terms of this stuff. So, we see that as if we try and shrink down time and shrink down this entropy number, this number of particles or number of things, or number of transitions, as we shrink both of those down to 0, well, as this goes to 0, then 2 to the 0 is going to be 1. 1 minus 1 is 0. This t is going to go to 0. So we're going to, at the start of our observation, the time is going to go to 0, because we're saying we're going to start observing now. So as you shrink these down to 0, then this energy that you're left with is going to go to the spin. Well, apart from a time factor, because this is unitless and this has units of time, so this would be over seconds or whatever you choose. But that numerically the energy goes to this as these things, as the time and the entropy. And when you start measuring, as that goes to 0, as you say we have nothing and we're starting our observation, we have nothing, no particles, no whatever, a vacuum, and we're starting our observation, the energy is going to go to this. And that's what people know as 0-point energy. It's as you have nothing, as you go to nothing, as the vacuum energy, you're going to have this. And this is really what's going on. So some people might call 0-point energy something else if the temperature goes to 0 and what's going on with that. But really, we'll see if the temperature is really 0, then something else is happening. So we can call this 0-point energy, and it makes sense, 0 point. Anyway, so at fixed time and spin, just hold these fixed, and we're saying it's a certain type of particle, it has spin whatever, and we're measuring it at whatever time. Well, then, if we're saying we're going to count particles, we're going to count things in terms of particles, like this is a thing, this is another thing, counting stuff as separate things, then if we're going to do that, energy is quantized. So if this is fixed, this is going to be whatever it is, and we're going to have it's a particle with whatever spin at whatever time we're measuring it. Well, if we're saying that things come in particles or in little lumps of things, if we're going to measure individual things, then energy is going to be quantized. And so that's the effect that we get in quantum mechanics when we try to measure things. And we saw kind of at the very beginning that what we call spin 1/2 or spin minus a half, people call it fermions, and they like to make up fancy names. It's just matter. That's when something's stopped, and we begin our observation, and we say, okay, this is what this is. And so, but what happens is they're parameterized by sines and cosines, as we did. We parameterized motion like that. So the sine is only, the angle can vary all over the place, but the sine is only going to be 1. It's only going to be 1 or minus 1 at certain points. So that's going to have the effect of when we try and measure things and stop them and measure them, then energy is going to look quantized. And that's what's happening with quantum mechanics. And that's why people think, well, it's just all, it's all random, and maybe there are just infinite number of universes and everything's going on at once, and let's, make movies with multiple universes and all this crazy stuff. This is all that's going on. It's not that crazy. It's not that out there. There's no weird different interpretations of quantum mechanics. We saw last board or whatever how it can be hard to predict. It's like throwing dice. I mean, dice aren't random. It's not just random, but yeah, good luck trying to predict the dice without, using a fixed die or something like that. It's, for our purposes, we might call it random, but it's not actually random. It doesn't mean that it's easy or that we can even predict it with a computer or a calculator or something, but it's not random. And this is really what's going on. This is how energy appears quantized. So you might be feeling like this, but, well, deal with it or turn the video off or something. Anyway, we're going to use complex numbers. We're just going to use this to recreate what people do in quantum mechanics. Complex numbers and imaginary numbers, they used to be all the rage, that's what all the cool kids were doing, using complex numbers. People were like, whoa, we can use these for stuff. And, it's like, dude, you can, but you're just making it harder on yourself and me. So, well, we'll do it. And this is I, an imaginary number, square root of -1. And no, it's no wonder that people get confused in quantum mechanics about these things, because they're obscuring all the actual concepts behind complex numbers. And really all complex numbers are, it's a different way to use sines and cosines. That's all it is, just a circle. And sometimes the math can get a little complicated, because if you're using a circle and you try and go to square coordinates, well, it's basically like trying to put a square peg into a round hole. It's you're going to have a little bit of trouble. So that's why you put things in terms of a radial distance and put things in terms of sines and cosines, because you can break up this r, this radius, this distance, into components x, y, and z. And we can do that later, and I'll show you how to do that with vectors. But we don't need to. It's just going to make things harder. So, well, let's jump into it and do it the way that quantum mechanical people do it, and show that it works, and derive all their stuff from conservation of motion, basic law of physics. So anyway, this is what they call the state function. It's you can parameterize it this way. It's a complex number, and the state function times its, or state vector, whatever you want to call it, times the complex conjugate is 1. They mean the probability is 1, and we'll verify that again with the quote coupling constants. But this is what this means, and we can work out the math. And if we put it in this form, if we want to say, well, it's parameterized by some sort of momentum and some position, and do calculus and take the partial derivative, then we get this. And we can say, okay, what was momentum again? Well, this is what it is. We can put it in this different form, just to get rid of the energy. Put it in terms of c, omega, h bar, whatever. And this is mass, and so we can multiply through by I and write it in this form that we're going to use. And now, if we take this cosine and just multiply it by this state vector, state function, then we can work out the algebra and write it in this form. Okay, putting it all together, if we take what's usually the case when you're doing quantum mechanics, it's going to be this times this state function, state vector. We can do a little algebra, work it out, and get it into this form right here. Right here. Now, what people usually do is just remove these psi's, these state functions, and put that on the outside and treat this p then as an operator. And if that's the case, then this part of the operator would look like that, just like the regular momentum operator that you're used to seeing. But you also have this term over here, this MC term. And that's why when people first started doing quantum mechanics, they thought it was just this. And then they had to make more corrections and make other equations like the Klein-Gordon equation or the Dirac equation. And then they also didn't have this in terms of just radial distance. They had separate x, y, and z. And when you do that, then and you're using complex numbers, then you have to include what are called Dirac matrices. It's just a matrix with sometimes imaginary components to try and deal with different components of the x, y, and z. And it gets more complicated, and you're just making more work for yourself. But this is what's going on. So just to show you this, and later on I'll derive a vector form for it so you can see that it's really the real deal. But this is what's going on, and let's move on. So, the mechanics part. Well, starting off, we remember that this was what omega was. It was just a way to measure energy, or energy is really just a way to measure this omega. This h bar is just units that we're choosing. And this omega is really the key thing. This is the angular velocity, and this is really the thing that people are realizing is some type of curvature. They're like, well, maybe space-time is curved or something. No, it's just your path through space has some curvature, and that's all this omega is. And so I'm just putting it this way so you can remember that. And this is that conversion factor we used. It's just handy to have around. All right, energy. We can also express it in this form. This is also sometimes called the Hamiltonian form. It's just the energy. And the kinetic energy part, I don't know why people insist on using T and V, I guess to make it more confusing so that nobody else can learn physics. But this is the kinetic part and this is the potential part. So then that makes it so the energy is just the kinetic plus the potential part. What this is called the Lagrangian. Really, it's just the poor man's energy. That's all it is. It's the kinetic energy minus the potential energy, and so it's this way. What people use this for, what they used to use it for, was simply as a tool. That's all this is. That's all this Lagrangian is. It's a tool to find the equations of motion. Well, we actually already did that. We found what force was and distance and velocity. We already found the equations of motion, so really we don't need this Lagrangian. But people insist on using it. People don't really understand why they're using it. It's like, well, it's just a tool to find the equations of motion. That's all it is. And people are amazed at all these different symmetries that they find and gauge invariance and all these different things when they really don't understand what they're looking at. It's the Lagrangian. It's all it is a tool to find the equations of motion. That's all a Lagrangian is. It's not the energy. It's kind of a poor man's energy. But it's just a tool. And you need to use the tool in the right way. I mean, use a hammer when you need to use a hammer. Use a saw when you need to use a saw. Don't try and do construction with a kitchen knife. I mean, you can if you really, really want to, but it's going to be hard. And we're going to see how that works out in particle physics and the standard model and all the Lagrangians that people are using. People try and find Lagrangians really by trial and error. It's just trial and error. Like they're throwing stuff at the wall and waiting for something to stick. And sometimes they hit on correct things, and sometimes they're off. And they're usually off by quite a bit. And it only shows up at, when you get at scales larger or smaller than the area that you make your theory for. So this is really what's going on, and we're going to go through and check and make sure that these really do satisfy the equations of motion, that this is, that you can use this tool, that this form of the Lagrangian, you, in the privacy of your own home, can, close the blinds and start math problems. So you can use this Lagrangian. This is the correct form, and we'll use it later. With quantum chromodynamics, for example. I'll show you all about that. Anyway, the Lagrange density is usually the form that people use it in. All it is divided by volume. It's just Lagrange per volume. And it's just this form. And you can see, I don't know, I just wrote it as a block L, so it looks different. But you can see that this is the density term again. And this right here, is the pressure, force per unit area, which we'll use in a little bit later on next board or whatever. Anyway, the Lagrangian is used in the action. The action, it's just something that people call, well, I don't know, let's call it action. That way we can say principle of least action. All it is an integral over this Lagrangian. So you put the Lagrangian inside the integral and you do calculus, and you do calculus of variation is what it's called. You can also do an integral over the Lagrange density, and sometimes if you want to put time and space into one whole thing and call it space-time, then sometimes this would be like d4x is how people would write it. So anyway, let's just call the action A, and position, people usually doing this derivation, they write x as position instead of r, but we know it's just this radius. And again, I'll go through the vector form of this so you can see, but this has x, y, z components. And we'll just call it x for now just to make the notation simpler. And the velocity, x dot for a time derivative is what people write often. And we know it's just the velocity v, dr, dt. But just to make the notation similar, because you probably recognize it in this form. Anyway, action, this is what it is. The action is just a function of position only. The Lagrangian is a function of the position and the velocity, or position and momentum. And people use this way because in the uncertainty principle or relation from the quantum mechanics, people get afraid, and so they use this form, and that's fine. We know what it is now. But anyway, we can go through and say, well, let's try and find the minimum of this so-called action, this least action. Well, we'll take the variational derivative, or the variation right now in this case. And so that goes inside the integral sign, and we can work it out. This is just like the chain rule. The partial derivatives going on. And so now what we can do is we can put this chunk over here, and this chunk use what's called integration by parts. It's just like this, do this, and you just break it up like this. So anyway, these are the endpoints of the integral of whatever we chose, and we get this. And so if it's a variation, then we want this new variation function of x or whatever to match at the endpoints. So we're going to take a path through space, or path through space-time, whatever you want to call it, and say, well, let's try and vary that path a little bit. That's what this is doing. Let's try and vary that path just a little bit, but we want it to meet up at the endpoints. Okay, well, if it meets up at the endpoints, then this is going to be 0 at both parts, this variation in x. So this whole thing is going to be 0. And so what we can do is put this together with this. This is 0, and it's this right here. So this variation in the action is this representation of the Lagrangian. And so if we say, well, if the variation goes to 0, if we're at a maximum or minimum, that really people are trying to find a minimum, but this will give you a maximum too. If we're at a maximum or minimum of this action, if we're trying to minimize this action, then that's only going to happen if this thing is 0. And that's only going to happen if you say this variation could be anything, and you're integrating, then the only way for this to be 0 is if this thing inside is 0. And so you get what are called Euler-Lagrange equations. People like to hyphenate people's last names and make long names for things. Just, I guess to make it really harder for people to understand what it means. But this is all it is. And this is supposed to give you the equations of motion. And so if you didn't really know what was going on with force and velocity and mass and all that business, then you would have to have a Lagrangian and say, well, integrate this Lagrangian over all space, I guess, and try and find the minimum. And so you would go through this whole thing. You wouldn't really know what you're doing, and you get these equations and say, oh, okay, cool, I can use this somehow. But the thing is, this Lagrangian thing is not unique. I mean, if you can multiply through by constants, you can add certain things in here as long as they're as long as the derivatives work out and match up. You can this thing is not unique, so you can if you want to find the correct equations of motion, so you can find the same equations of motion from all sorts of different Lagrangians, and that's why people encounter things like symmetries and invariances and all these different types of things. And that's also why when you go through something like Noether's theorem, or however they want to say it, when you go through something like that and you're looking for a conserved quantity, something that doesn't change with time, then you find something like this omega right here. And so what they find is oh, well, all the conserved quantities that we're finding look like angular momentum or angular velocity. And they actually call it a Noether charge, and that's what charge is in like electromagnetism and that sort of thing. They say, well, it's just this angular momentum. It's something is spinning somewhere, or at least that's what it looks like mathematically. And so that's where they get this. And they use all sorts of different Lagrangians, so they think that there are all sorts of different omegas or angular momenta all over the place. And so that's really the basis of physicists imagining that there are extra dimensions, because they have these different Lagrangians and they find these conserved quantities, these things that don't change in time. They don't realize that they're looking at the same thing. They think they're different things. They think they're different charges. They think it's electric charge, or then they come up with a weak or a hypercharge and all sorts of, and color charge, and they just name it pretty much arbitrary things and say, well, it looks like some sort of angular momentum, and mass looks like some angular momentum too. Huh, that's funny. So there must be extra dimensions that these things are spinning in. So that's where they really come up with this idea for extra dimensions. And there are a few other reasons that they come up with the idea for extra dimensions, like in supersymmetry, dealing with Grassmann numbers and anti-commuting and different things like that. We'll get into that. But this is really what's going on. And they think they don't recognize that this is the same thing, the same omega. And to try and rationalize that or deal with that, they say, well, maybe there are extra dimensions. And why can't we see them? Well, because they are probably really, really puny and we can't see them. I mean, if you didn't know this, if you didn't know what was really going on, then sure, you might be led to the conclusion, well, the only way to get it to work mathematically is if there are extra dimensions. And yeah, or you're really looking at the same thing all along. So, I mean, I like science fiction sometimes, and it's cool, but, we don't see extra dimensions, and, this is why. This is what's going on. So this is the complicated math for it, and anyway, we can check what's going on with the equations of motion and really verify that this is the force we found earlier was force, and go through it. So again, F equals ma, blah, blah. We can use the conversion factors, find this form. Oh, fancy that. There's a r squared in the denominator. The, the inverse square of the distance relation between a lot of forces that we see. That's because you can write force in this form. You also have this alpha up here, which we're going to
explore when we go through electromagnetism and other things. So that's why a lot of times things look like it's an inverse square law with the distance, because usually it's at fixed velocity or low, or at least low velocity, so this part, this alpha, doesn't really come into it, or they just take it from a certain region or a certain scale so it looks about the same, and then they throw a constant in there and say this is constant, just like that gravitational constant, supposed constant that we were dealing with earlier. This is really what it is, and this is also called a coupling constant. It's not really a constant, of course, but particle physicists, they have these different, quote, coupling constants, and what they do is they run, is the term that they use. They change, and when they graph it out and they plot it out, they see that, well, when they vary the energy levels, when they change this R, or really the energy, when they vary that, at some point it looks like the forces all run together and become the same thing. It's like, that's because they are the same thing. They've been the same thing all along. All you're doing is taking different slices of this relation right here and imposing your own idea of what this alpha should be, and then you're trying to figure it out from there. And you're saying, well, wait, what's going on? It looks like they all run together at the same point. They are the same thing. They've been the same thing all along. And we're going to go through that and see how that generates things like thinking that quarks have 1/3 of a charge and all that stuff that's going on with that. Anyway, we can work this out, and well, this is one form of force. Work out distance and put this in terms of the sign and whatever. And remember, we can just multiply r by gamma, and it just removes the time dependence. So all it is kind of a way to write distance. It's not true distance. It's just a way to represent kind of invariant distance. If this was 1, if this gamma was 1, and your time was completely synced up with the observer's time, the target time and observer time are exactly the same, this gamma would be 1, and so this is what distance would be. And you can see that just by inverse of energy. And we went over that, how it looks like it would be the Big Bang with 0 distance. If you have 0, then it would be infinity in the denominator, and back and forth. And if you go to infinitely far away in space in either direction, then this looks like the energy goes to 0, and that sort of thing. That's all this is right here. This is just a constant. This is actually just a constant, just like, well, it's as constant as much as energy is a constant in time. It doesn't vary in time. So we can say, oh, well, we can use that. What's alpha? Put that in terms of the gamma, and put that in terms of this. Okay, now we write what force is. Use that. We can just do a little bit of algebra, and we get this form right here. So this down here, this r cubed, that's just like the energy. It does not vary in time. So it's a constant with respect to this, really. So this is, again, that timing factor. And so we can plug that in to the potential energy. And I don't know why people call it V, just to make it confusing. But the potential energy we found out much earlier was this. Then you can also write it in this form. And so, doing the little algebra, we find this right here. And so if we use this in the equations of motion, they take the partial derivative. You take the partial derivative of this Lagrangian with respect to r, well, this is going to be 0. This does not vary with r. So this would be 0, because by the way, this removes the time dependence that in m. So this does not vary with r. So the partial derivative of the Lagrangian with respect to r, this, again, we just use this to represent r here. Partial derivative of the Lagrangian with respect to distance is going to give you this, minus twice the force. Usually, people using the Lagrangian try and do this fancy business to find the force. That's all they're using it for, is to find this. But what happens is when you use the actual Lagrangian as you define it in terms of energy, this is what the energy actually is. It's not 1/2 mv squared. It's mv squared gamma. And if you say that's the kinetic energy and potential energy, and say the Lagrangian is the kinetic energy minus the potential energy,
Well, what that means is that when you work it out, when you actually work it out, and you remember that you need to include these gammas and you need to make sure you know what you're doing, then you're going to get this minus twice the force. And that is why if you take the other one, if you take this part here, you're going to get, if you keep a 1/2 mv squared, if you take the partial of this and then differentiate it again with respect to time, you're going to get 2 ma with a minus sign. So that means that you're going to get the same equations of motion. But if you try and go through and get the equations of motion, you're really going to get this. And it doesn't affect, it doesn't, I mean, you can multiply this or divide this Lagrangian by a factor or by a constant or add something in here which jives with the derivative here. And it's not going to change your equations of motion. That's all the Lagrangian is, a tool to find equations of motion. And if you don't have this tool right, or if you're using it wrong, you're going to come up with the wrong answer, and you're going to see things, other terms of force in there that you did not account for, and they're going to look like tons of different forces, and you're going to think that there's supposed to be a Higgs boson with a certain mass, and it's because your equation is wrong, and when you say that the Higgs boson is supposed to have this certain mass, it's because your equations are wrong by that certain amount. That's why you find a certain mass like that. And it all comes from this Lagrangian. And so this is the correct way to use a Lagrangian. And this is the correct way to use a Lagrange density. And I'm going to use that when I show you quantum chromodynamics. Anyway, that's this, and let's keep going. So here's a bunch of math barf up on the board for you. But I just want to go over some stuff, vector stuff, and some stuff having to do with rotation and curvature and all that business. So just starting off, these are some equations we can use to do stuff and things with, I guess. Anyway, this is a vector form. This is the radial vector that we can use to do stuff and things again, which we'll use this for electromagnetism and whatnot. Anyway, this is the magnitude of this radial vector, showing that it's really the radius. This is the partial derivative with respect to x. Yeah, same for x, y, z from this relation here. This is the gradient operator, or the del operator, or whatever, and we'll use that later. And this shows that this r hat, this unit radial vector, is actually, in our case, just the gradient of r, of the regular scalar r, not the vector r, the scalar version. So we can use that. And this total velocity vector is this, and we'll use this in just a second. But I want to draw your attention up here to, this is just a trig identity. I always remember it by sick cats positively can't sing. Poor sick cats. They can't sing at all. This is how you would pull this apart. And again, this is just what theta is. And you can say, well, all right, let's look at this alpha, it's sine squared theta. And write this out, this messy looking thing. And then square it and say, all right, r squared. Yeah, here you go. If you're a pirate, you'll like this little equation. R. Yeah, it's pretty awesome. Anyway, this is how you decompose these things. And if you square this r, this is what you're going to get in terms of stuff we already know. I mean, you could put whatever you wanted in here to make it, to pretty it up. But this is just what it's going to be in terms of things that we already know. For instance, the omega, the time, and the initial angle, or the spin, energy, time, and spin. So that's what this is. And we can see how the spin uncertainty relation thing gets into it, because if we're starting our observation, we're going to say we're starting our observation right now, then time is going to be 0. We're going to start there, time 0, from wherever we're starting. We have to pick a starting point. So if that's the case, well, this is going to be 0 inside here. The sine of 0 is 0. And so this term is going to be 0. And sine of 0 is going to make this whole thing down here 0. So, but the cosine of 0 is going to be 1. So in here, this will just be 1, and we'll get this nifty thing in here. So that means if you try and put this in terms of r squared, take this big R, which is just a constant factor with respect to the energy, just a constant with respect to time. It's a form of way to write the energy. So if we multiply this up here, it's just a constant factor, and we try and parameterize this radius, this radial distance, in terms of, this is just the Pythagorean theorem, x squared plus y squared plus z squared, in 3 dimensions. If we try and parameterize this, then what we're going to get is we're going to have to build it out of stuff like this. So at most, the best case scenario, if we're starting our observation, we're only going to get one component, one of the spatial components. However, we decide to say maybe this is the x direction, that's y, or that's x and that's y, or that's x, and however we decide to do it, at maximum we're going to get this a measurement from the spin, remember, in only one of these components. And so that's really what's going on with the spin uncertainty relation in quantum mechanics. It's just this. And again, if you want to do it in quantum mechanics form, then you need to use Dirac matrices because it mucks everything up otherwise. So this is the way this is a different gamma than this one. This is just, people always write the Dirac matrices of this gamma mu, and it goes from 1, 2, or 0, 1, 2, 3. And then they have a gamma 5, which is like all of them multiplied together or whatever. Anyway, and also tensors, if you want to put it in tensor form, then you're going to have this capital gamma, this big gamma, or the Christoffel symbol, which will then, out of these, you can build the Riemann tensor and the Ricci scalar tensor, and then out of that you can build the Einstein tensor, this fancy G. And we saw before that that from just conservation of motion, you can derive, and the fact that the supposed gravitational constant is not a constant, we can derive the whole general relativity from that and show that it's not quite right, show that it's off. And when it's off, then you need to make corrections, and then you're going to have curvature corrections in here because it's going to come from this omega, or the omega, where is it? Somewhere around here. There, the omega. And so that's going to be this curvature. It's going to show up in this form here. And so we're going to see that in just a second. So the total velocity vector, it's just the time derivative of the radial vector, and it's this. Say, oh yeah, well, that's the total space derivative, or arc length. I didn't put just an s, as people normally do, because I used s for spin. But this is the time derivative of space, and this is the kind of norm of it, or the magnitude of the vector. And we remember from the beginning that we said this is c squared. And that's what they do also in special relativity, or, well, not, I guess, special relativity, but relativity in general. Special relativity, Einstein noticed it was a mistake, and so he tried to correct it with this, but this just makes it more confusing. It's still not quite right. So it's really just this right here, this conservation of motion. So we can put this in vector form, and whatever floats your boat. The radial vector, the radial velocity, the thing that we normally just call velocity, is this. And so if we want to break it up into vector form, we can pull it apart, and notice just from calculus, this thing, we can say that, oh, this is this gradient looking thing on r times the dotted with this total velocity vector. And the dot product is just the magnitude of these things times the cosine of the angle between them. And we remember the magnitude of this is speed of light times cosine, then that gives you the back the same thing. So it's just another way to write it, and we'll use that when we do things in fields instead of just ordinary whatever scalars. We can use it in fields and then put it in this form and work with it. And do quantum field theory and make it sound super, mysterious and exciting. And it's really not. It's just this. And we can likewise do the same thing with the curved part of the velocity, your part of your path that's curved, and put it in this form. And it's just the magnitude of the two things times the sine of the angle between them. And that's the cross product. So it's this way. I mean, depending on how you define which direction you're going, this can be plus or minus. But we're going to use this too. And so this is, again, the magnitude of it is this. And so we could use that and say, well, all right, if we put this in differential form, we're going to get this. And if it's just 2 dimensions, then this is going to be much simpler. But in 3 dimensions, we say, oh, well, I guess you could say we have separate rotational components in each of the 3 directions. Okay, well, you put it in vector form and do it that way if you want to. Or you can just say, well, it's going to have a radial component and then a component that's not radial, that's along the same angle. And then the hat just means a unit vector, and that's all that means. So we can use this, we can use this, we can use all sorts of stuff. So I'm just smacking you in the face with a bunch of math and equations and stuff, just to, see, just to weed out the faint of heart. Not really, but this, like this stuff, if you actually know what you're doing, if you're actually a particle physicist or a nuclear physicist or whoever, or a mathematician, like, I should not have to hold your hand and go through all of this. You should know this. So if you don't, look it up, and I'll use some of this later. But this is just to throw it in your face and say, well, we might use some of this, and if anything dawns on you, you can, whatever. But here you go. We'll move on and get to some more interesting stuff. So on to thermodynamics. Remember, these are the representations or formulas for energy and momentum and mass and whatnot, force and acceleration. And the velocity is just the rate of change of your radius or your distance outwards that you're measuring with respect to time. Acceleration is just the rate of change of your velocity. So if you're speeding up or slowing down, and F equals ma. So this is an expression for the energy in terms of the force and whatnot. So we can also write the kinetic energy. For some reason, people write T for kinetic energy. It's this. We can write it a few different ways. And potential energy, again, for some reason, people write V. So we can write the potential energy a few different ways. And the total energy is just the kinetic plus the potential, and that's the energy. And then the Lagrangian, the poor man's energy, is just the kinetic energy minus the potential energy. And so we can write it like this. And from the, quote, Euler-Lagrange equations, and I'm surprised nobody's decided that that name needed to have a few more hyphens with other people's last names in there, like the, what is it, from cosmology, the Friedman, Robertson, Walker, Lemaitre. Like, are you sure that's it? You don't want to, like, add all the names of the Ninja Turtles or something to that? It's... You can still fit it on one line. Why not make it even harder? Anyway, it annoys me. So these are the equations that give you the equations of motion, and so we can go through that. And this is the derivative of the Lagrangian with respect to velocities twice the momentum. If you're using the actually correct Lagrangian, then it's going to be 2 times the momentum, and the derivative of the Lagrangian with respect to position. It's going to be this. It's going to be twice the force times gamma. I think last time I forgot to write the gamma, but seriously, if you recognize that or knew it was wrong, then you should be able to just you should be able to just take the equation that I gave you at the very, very beginning, the conservation of motion, and derive everything else. So I'm too lazy to go back and record a new video, but this is what this is. So the Lagrangian because it has minus the potential energy in here, then you're going to get minus minus, so it's going to be plus. And the reason why people use the Lagrangian to figure out this, quote, principle of least action and not the energy is because if you plug in the energy, then you're going to get a minus sign up here. So that's the only reason people use this instead of this. It's just a tool. That's all this is, a tool to find the equations of motion. And we can verify it. All it is the Lagrangian is a tool to find the equations of motion. This is the, quote, equations of motion. And it's real simple here because I'm not breaking up the distance into x, y, and z. I'm just keeping it in the radial form. And so that's real easy. It's just this. And you can also see how people would get confused or assume that they needed to have, instead of, that in order to have this, that they can go from this. If they were going from this and integrating, going backwards, then they would get 1/2 mv squared for this, and they would miss out on the gamma. And also, they would think that this would still be minus the force times distance. That this is what the potential energy would be without the gamma, because they wouldn't recognize that if you take the derivative of the Lagrangian with respect to position, with respect to distance, you're going to get twice the force times this gamma. You're going to get twice this. So normally they don't see this. They think force. They think that the force in this case is not a function of position when it really is. You can we worked that out last time. So what they're going to do is they're going to take the partial derivative of this and just be left with if it's minus the potential energy, then they'll just be left with plus the force, and then they'll say, oh, well, that means the kinetic energy should be 1/2 mv squared. No. It should be this. And you can also see why multiplying this Lagrangian by any constant factor, or dividing by any constant, is going to give you the same equations of motion. So you can, write home to your grandmother all day long about all the symmetries that you're finding. No, it's just this. This is the equation of motion. And it's just, you can do whatever you want with the Lagrangian. You can even add or subtract certain things as long as they fit into this relation here. And so that's like gauging and different things like that. So anyway, moving on. Pressure. It's like force per unit area. But the reason I put pressure like this with the gamma in here is to adjust off a certain time dependence for this force. Meaning we can still have pressure and hence potential energy for things if this gamma gets messed up. If we have something like a photon, which is moving at the speed of light, then we can still talk about like photon pressure or radiation pressure or whatever else. So this is a way that it works for both. And remember, if something's at rest, or if it's at rest, then this gamma is going to be 1. If it's moving slowly, then the gamma is going to be about 1. And that's why in classical physics, you don't even need to worry about this time dilation factor or whatever you want to call it. You in classical physics or whatever, you usually don't need to worry about this, but this is what you need to include if you want it to be right. Anyway, we can see the volume is just this. So the pressure times the volume with a minus sign out front is the potential energy. So I guess you can use the V to remember it by, I don't know, whatever. I try to put a little curly Q on it so you don't get confused with using all the same letters, but I get confused sometimes. But anyway, the entropy, I'll use a squiggly S thing, again is this. We worked this out last time. It's just the Boltzmann constant. All it is conversion between, it's like converting between inches and centimeters, and in this case it's between energy and degrees. So that's all this is. It's nothing magical. I mean, if you want to do magic with it and like make a dove fly out of this number or in the shape of this constant, then go right ahead. I don't know how you do that, but you have to wrap the poor dove up into all sorts of little parts. But don't do that. Don't be mean. The dove wouldn't make it. Anyway, temperature, it's just really, you could say it's the average kinetic energy. It really is. It's the kinetic energy here divided by the number of things, the number of particles or whatever you want to count here by this. It's really the average. So the typical thing that people are told, temperature is like the average kinetic energy. Yeah, you could say that. And so I guess this T kind of makes sense to have it there, whatever. But we can put this down in this form for the total energy. And so we have energy, temperature, entropy, pressure, volume, whatever, good deal. You might be saying, well, wait, you're missing tons of stuff. There should be like internal energy and Gibbs free energy and like all sorts of other, factors and things that you need to add in here. No, actually, really those come from the misconception that this kinetic energy should be 1/2 mv squared, and that this is really what it is. This is all it is. And we're going to actually look into this a little more and see exactly how phase transitions work. Whoops, actually, this is a minus sign here. I'm not going to go back and record that whole thing because I'm getting tired. I'm going to just keep moving on. But this is minus. We'll use that in a second. On to phase transitions. Again, this is what the energy is in terms of temperature, entropy, pressure, and volume. I wrote the minus sign correct this time. Good for me. Anyway, I decided to put it in block lettering, so I'm not, well, I don't know. It's irritating because all these different things start with similar letters, so whatever, I guess we'll work with it. So here's an formula for temperature. So we see it's kinetic energy divided by this entropy, really divided by the number of things times this Boltzmann constant, which is it's just a conversion factor, it's a conversion factor between energy and degrees, or between h bar and degrees. But it's just like saying inches versus centimeters and converting. That's all that is. So this is entropy, and this n, this was really the thing that entropy is this expression right here. So it's the log base 2 of this thing in here, which usually people think is supposed to be an exponential function, and it's close to it. It looks like an exponential function when this quantity here is small. Especially when you start out when time's 0 and then you move up from there, it's going to look small. But there are a lot of problems with people not recognizing this right here. We'll see that in a second. This is pressure, so kind of force per unit area with a correction factor. And this is the volume. So the old school version, not the movie, but old school thermodynamics, is it says internal energy is this U thing is this, and enthalpy is with an H for some reason, for enthalpy, I guess, I don't know, is this thing. And the Gibbs free energy, quote free energy for the world, yay, is supposed to be this. But wait a second, we know this is really the energy, so the internal energy is the total energy. So that would make this be the case, and this enthalpy would just be this kinetic energy, really. That's all that is. Kinetic part, this is the potential part with the minus sign in it. So that means that this thing is really 0. But if we think that this kinetic energy is supposed to be 1/2 mv squared with the gamma, then this g would end up being this, would be half of it, would be the other half. And furthermore, since that's what temperature is, or this is temperature times entropy, or really NK times temperature, then this part would look like N times some crazy looking thing, a mu, or a chemical potential. That's what it would look like. It would look like we needed to add in an extra thing with a chemical potential, which depended on the number of things. And so that's what's going on right here. This is what's going on. And so the old school phase transitions is when people said, well, this delta G is 0, meaning the change between these, or the change as this thing is changing, it should go to 0. Well, okay, if we think that we're supposed to have this G, if we don't realize all this, and we think it's supposed to be, we're supposed to have this G, well, then what is this? This derivative, we can find this, take the derivative of it, and do the little algebra or whatever, and we see this 2 cosine sine. Wait a second, that's what we remember from this quantum mechanics stuff, uncertainty principle, whatnot, momentum times r. And that times, with this energy in front, this is a factor which is constant in time. Constant in time. The energy is constant in time. So this whole thing is constant in time. This thing, we can throw one of the omegas in there, and we have to compensate with an omega up here. That's why it's e cubed now. And put the 2 down here with it so that it matches the angle inside here. This is 2 theta, and I just wrote what theta is inside here, this angle. We say, oh, well, this would match up. So we need to make sure that the 2 is in here with this, and 2 is with this. And this thing, this big burrito here, we can call that a new distance, a different distance. So if the first distance is in terms of this sine theta, Well, then this new distance is in terms of this sine 2 theta with the appropriate 2 omega in front. So we say, well, this is what's going on at a transition. A transition. This new distance is 0. The transition happens when this thing, the derivative of this g, is supposed to be 0. And that means if this thing is 0, the only way for that to happen, without the energy being 0 or whatever, is if this new distance is 0. That's things coming together or breaking apart when the distance between them goes to 0. And that's why you can transition. That's what's going on there. That is what's going on. And to look at that a little more clearly, well, if we want this to be 0 at time 0, then this theta is going to be 0. So what that means is, well, we can write down what theta is, either in terms of this entropy number or in terms of time and spin and whatnot. Well, if this angle is starting off at 0 for this new distance, then, well, the only way for this part to be 0, for theta to be 0, is if this s is 0. And that means, well, this n can vary. It could be anything. It can be anything. And so that means, what that means is that if you look at something during a phase transition, you're going to see self-similarity at all distance scales, because you can put this n in terms of other things, in terms of the energy and whatnot, and the energy in terms of distance and all that good stuff like we've been doing, and you can see that it's going to look the same at all distance scales. That's why if you, under a microscope or whatever, you look at the phase transition between like a liquid and a gas, it's going to look like droplets of water inside bubbles of gas, inside droplets of water, inside bubbles of gas, and smaller and smaller. And it's going to look like that at all distance scales, And that's because of this, what's going on with the entropy, this n, this number, this counting of things that you're looking at, whatever. That's what's going on. And that has to do, we, again, saw how that has to do with chaos theory and the fact that, well, if you've got this exponential here, this 2 to the power, well, that's going to grow exponentially. That's called sensitivity to initial conditions. And since this is an angle, and this is inside a sine theta, and we did the original sequence of the sine squared, so that would stay between 0 and 1. This one would be between -1 and +1. It stays bounded. The values that you measure stay bounded, and that's what's called folding. So you have sensitivity to initial conditions and folding. So that is what chaos is. So it's not random. It's not random, but it doesn't necessarily mean you can predict it. It's kind of like trying to put all the digits of pi into your calculator. Well, you can't. It goes on forever. But you know what it is. You know it's the ratio of the circumference of the circle to the diameter. So with that information, I mean, you can write all sorts of, you can calculate as many digits as you need. But if it's something like this, if your calculation grows exponentially or whatever, the error is going to grow pretty fast too. So it might not necessarily be what we would call predictable. So also, this is what will give you fractal patterns. That's why phase transitions look like that, and all sorts of other things. Whether it's a transition between something that we would call the vacuum, meaning like empty space, or what we would think would be empty space. Well, we can call something empty or stopped or photons or matter or whatever, depending on these things, depending on these trig functions here. Depending on, remember how we define distance and velocity. So those can vary. We just say at the start of our observation, time is 0, and so it's going to depend on this spin. But then as time goes on, it can be anything. It can, this angle can go between all sorts of things. And so that's going to look like if we stare at what we would call the vacuum, it's going to look like particles and antiparticles, and the kitchen sink is popping in and out of existence all the time in this quantum foam. That's what this is going to look like. And it's not going to be predictable the way we think. And so people are going to say, well, maybe it's random. Maybe, we've got all these different universes and we can make a movie about Jet Li fighting himself, which that was kind of cool. But this is really what's going on. This right here is what's going on. And so again, n can vary all over the place of this 0. And so that's what we see. We see self-similarity at all distance scales. And so that's what's going on, guys. Now we'll keep going. All right, I just wanted to stop because I realized how long this took. I didn't think it would take this long, but what did I expect? I guess we're going through everything in physics. It's pretty big. And I mean, I'm not a physicist or a mathematician or anything. I'm nobody. But anyway, I figured, and I don't publish anything or whatever. I never have. But I just figured this was kind of too important. I had to just let the world know. So I guess either everybody will love it or everybody will hate it or try and steal it or ignore it or come crucify me for saying there are no black holes. When I mean, I'm not against anything. I think plenty of theories are cool and it's interesting to look at and whatever. And there are tons of smart people out in the world and a lot of people smarter than me. But anyway, here it is. These are a lot of the equations that we used, and so this is just for you to see and remember, and you can use them to do stuff and things and what have you. But congratulations on making it this far. I'm surprised you haven't turned the video off, or maybe just skipped ahead to this part or something like that. But whatever, congratulations. Woo, high five for you. That's a high five. I'm tired and hungry, and I really don't like doing this. Well, I mean, it's kind of fun, like going through and telling people, but I wish I could just magically, I don't know, teleport things from my brain into your brain. And by the way, teleport, I'm not really sure if it's possible. I guess the only way to do it would be to smack something with the opposite charged things, what we would think of as antimatter, and send it off as a light beam or something, but that would be kind of dangerous. I really have no idea how to do that, but I don't know. It's fun to think about. But I guess we'll finish this. What do I have next to do? I'm going to get into, let's see, thermodynamics. Or no, we already did thermodynamics. Fluid dynamics. I'm going to do with some vectors. I'm going to do electricity, magnetism, and then go into actually nuclear forces and see what's going on and unify those. So then after that, I'm going to go and show you how this is connected with like entropy and things like that, how that's connected to prime numbers and the Riemann hypothesis and whatnot. So we're going to hit Navier-Stokes, Yang-Mills, and Riemann hypothesis. And I'm just going to do it quick. I really don't want to spend much time doing this. If you are actually a mathematician, then you, in the privacy of your own home, can turn out the lights and start math equations. Because I mean, I shouldn't have to hold your hand and walk you through everything if you actually know the equations and you're like, no, that's wrong. It's like, well, why don't you go through and check it and make sure, I mean, there are probably many points in here where I'm wrong and just too lazy to go back through and fix it all. And I mean, hey, with my notebooks, I do that all the time. I cross stuff out, and I don't know. There's a whole bunch of stuff crossed out in there. That's just the way it works. But anyway, this is up to you. Just knowledge for you to have. So it's not like you're paying me anything to watch this. It's not like I mean, if you're upset with it, so what? I'm so sorry. It's like you get this information for free, and but again, I couldn't really keep this to myself. That'd be kind of a jerk if I just left this in a notebook somewhere and didn't tell anybody. But anyway, well, enough of that. Enough of my complaining. Let's move on. All right, just go over a few things. Again, this is what the temperature was, the kinetic energy divided by the entropy. And it's this thing. And this is the expression for the entropy down here. This just expanded out, this n, this number or count of things. And again, it's this. And
people misunderstand or think that this is supposed to be an exponential function, which it looks like an exponential function when this thing is small, but it's really not. It's this. And this, since this is temperature and this is in temperature and this is in the denominator, when people expect this to be much larger, to be an actual exponential function, they'll expect this to be much larger, and they will expect this denominator then to be much larger. And if the denominator is larger, then guess what? The temperature is going to be lower. The temperature is going to be lower if this denominator really is bigger. So what happens is then if this denominator is bigger, then the temperature is going to be smaller. But if the temperature is much bigger, then that means much bigger than they think. Then that means the denominator is smaller than they think. As this denominator shrinks way, way, way down, then this whole fraction gets much larger. And so that's going to give you a larger temperature. And this is exactly what's going on with like the corona of the sun. And people are like, oh, what's going on with that? It's violating thermodynamics. And well, first of all, I mean, with entropy, this is what it is. So you can't really say the laws of thermodynamics are set in stone. I mean, we know that they're statistical, and but this is what's going on behind it. And this is why they'll think that they're getting all sorts of weird measurements and this and that, and they don't really know what's going on with the physics of the sun. I mean, it's in the sky the whole day, during the day, not the night. Well, during the night for other people, but I mean, this is what's going on with that, and something that people have been looking at ever since people have been around. So that is what is going on with that problem. Anyway, moving on. Well, I'll remind you of this one, the gravity factor. It's not a constant. It's not a constant at all. It's this expression, and we can rewrite it in different ways like this. So we can put it in terms of this quote coupling constant. We can see how it, in the parlance of particle physics, how it runs. But it also has this energy in here. And that's why when particle physicists try and graph the different running of the coupling constants, like running of the bowls or something, I don't know. The gravitational factor is, goes off at some weird curve, and that's why, because it's got this in here, this energy down in the bottom, as well as this alpha. And so anyway, last time I mentioned about the Gibbs energy and phase transitions. I just wanted to write down this again and show you, well, instead of putting it in terms of some new distance, you can put it in terms of the old distance. There is just as fine. And then you're going to have this, the derivative of this goes to 0, or a change or a maximum or minimum in this thing, a phase transition, when, well, any one of these can be 0. So you could have, well, nothingness or 0 momentum. It's stopped, two particles looking like they annihilate and become a photon, or a photon splitting up into particles, whatever. It's you can have phase transitions all over the place. All right. So talking about energy scales is what particle physicists do when you're trying to measure something or measure interactions, particle interactions. Then you're trying to measure things on a very small scale, and as you try and measure things on a small distance, then this energy is going to get big. Right here, like you try and bring this down smaller and smaller, then this denominator is going to get bigger and bigger, and vice versa. If this gets really big, then this is going to get really small, and so that's how people try and measure things on a small scale, like wavelength of light, and we'll get into light a little more. But short wavelength light is much higher energy, much higher frequency, and so well, that's one reason that things more higher energy photons can pass through things more easily. Just like that's how people get X-rays. I mean, they're light, it's photons, just with more energy, lower wavelength, so it's harder for them to interact with things. And that's actually the deal with what's really going on with neutrinos. People, if something is actually, we'll see this in just a second, but if something actually has zero charge, really zero charge, then it's just light.
And the fact that you might think or calculate that it's going to have different masses or whatever is because these quote coupling constants are wrong, and you're forgetting, you're not taking into account other forces. And so you're going to think, oh, well, this Higgs boson is something special, like we'll measure it at, whatever whatever particle interaction we're going to measure it and say, oh, it's there. No, it's just light. It's just light. We went over that and showed how the forces, if something emits a photon away from you, the rest of it moves towards you. And so that's going to look like the photon emitted or whatever had spin 0 or spin 2. It's an equivalent thing. So people think, oh, these gravitons and these Higgs bosons, they're all separate things, but they look like they have to do with mass and they gravitate. No. It's just light. That's all it is. It's just light. And when your equations are wrong, when your Lagrangian's wrong and things like that, when you think there's supposed to be 1/2 mv squared and all that business, then yeah, you're going to get the wrong answer, but you're going to consistently get the wrong answer. So, well, depending, if in this case with this gravity factor, you can see that that's wrong because people look out and say there's dark matter. And not only do they think there's dark matter, but they think there's like 70% dark matter to regular matter. So that just means that the equations are way, way off at that point. Way off. I mean, then even further, even beyond that, when you get to even larger distance scales where this gets whacked out even more, then people say, well, there's this dark energy that's the rest of stuff that's contributing. And so, then the universe is almost all dark energy with less dark matter, but then just a really smidge of, like, really bit of matter. And it's like, no, it's not that at all. It's your equations. Those are wrong. So, I mean, it's like, oh, well, this dark matter, it doesn't interact with anything. It just sits there. It's, neutral, but we know it's there by the, because it gravitates. No, it's just the fact that your equations for gravity are wrong. And so when you correct that, it all goes away. And it'd be cool to put dark matter into science fiction and whatnot, but, leave it to science fiction. We got to look at what's in front of us. If it's not there and it doesn't interact with anything, it doesn't make any noise, it's like, well, maybe it's not there. It could be there, but we need to check. And so checking, at least with the math, we can see, nope, it's not. And this is why. So same thing with the Higgs boson, same thing with gravitons. So I'll go through some of the forces and show you exactly how that works. So renormalization group theory, to see that this is actually what they would normally call a coupling constant, we can do a little calculus on it, put it in this form, and rewrite it a little bit into the form that renormalization group theorists, I guess is what they call themselves, I don't know, would see it in this form, the derivative with respect to this weird looking thing, ln r in the bottom, natural log, equals some function times the coupling constant itself. So they would put a beta here usually, the some function, but really the true, quote, coupling constant, this actual alpha, the full thing, is just this. This is the relation. But if you have unknowingly split this up all over the place into different, and trying to force it be different forces, then you're going to get different beta functions in here, different beta functions or whatever. And then it's going to be hard to calculate because you got the natural log and this is a trig function. And so usually when people represent it, they're just going to put it as a power series with a bunch of different, like as polynomials that just go on forever, and they'll just cut it off at some arbitrary point and say, oh, well, this is the beta function. And it's like, no, it's not quite because, well, you're missing tons of terms. So that's another thing you need to keep in mind. And so that happens in renormalization. And then you also, since it's a trig function, you're going to deal with the Riemann zeta function. And complex, because you're trying to put a square peg into a round hole, and you're going to deal with trig functions, and you're going to run into that, and you'll see exactly how. But anyhow, electricity and magnetism. So this is the, quote, fine structure constant, not a constant, and this is the, quote, fundamental electric charge, just the charge of an electron, and this is factor. So this whole thing is supposed to be unitless, and it's supposed to be a coupling constant, quote unquote, and at everyday values that people measure things, supposed to be about 1 over 137. But again, it varies. It runs is what the term is. It runs, and so it varies. So it's not a constant. But this part is. This is from Maxwell. He wrote this out and said, "Whoa, hey, the speed of light, light's electromagnetic waves." So this is the I don't know, electric constant, magnetic constant. People call them various stuff. Permittivity, I don't know, permissivity, like, I don't know, horrible names. But this is just electric constant, magnetic constant, speed of light. And so, I mean, you could say, well, maybe that's not constant. Well, look, I mean, you got to pick something to be constant. I mean, you're just going to make more trouble for yourself. So you can say, well, these are constant. We'll use that. And then, well, this charge up top, we know that varies. We can write it as Q because, you know, in physics we'll say, well, or not me, but you or whoever is a physicist will say, charge, you know, things can have different charges. And so we're going to put that there. So the general form, the actually correct form for this alpha, not this fine structure constant, which is not so fine after all. I mean, look at this. This is a little messy, not so fine, kind of ugly. Anyway, this is the form you'd use it if you're going to do electromagnetism, and we'll use that. So you can see, you can take the derivative and whatnot and do this business, and you can see, well, this is really what Q, or charge, is. This is what charge is right here, times this. It's just sine theta times this constant, or we can put it in this form too. A little prettier. And so we can also see, well, if the velocity, which is c cosine theta, if this goes to the speed of light, so this cosine is plus or minus 1, well, that means the sine is going to go to 0. And that means the charge is going to go to 0. That is why photons don't have charge. That's why light doesn't have charge. This is it right here. This is what's going on. So we can also, if we want to get crazy and do quantum physics or quantum mechanics or quantum field theory. Field theory is just, all it is including vectors. It's like saying, well, it has a value now and a direction in space. So it's really not that, it's the same thing, just with a vector, and we'll do that in a bit. But this is the way to put it in terms of like a state vector and complex numbers, and so you can say, well, this is what it is right here. And of course, the complex conjugate times the state vector, whatever, is 1. Total probability is 1, whatever. And so you can do that down here. You can turn this into an operator, bam, on Q, the charge. And then you can also say, well, maybe it's a state vector in a way. And you can throw this in there too and treat it as a state vector, treat this as an operator, transform this a little bit into like a covariant derivative or a tensor derivative, or gauge potential, and we'll do that in a little bit. But this is just one of the things you can do. But this is the fundamental thing right here. This is what the charge is, and you can see it's just related to this. And you can also see that it's a probability, and you know, particle physicists know that this thing really represents the probability that the electron will emit a photon. And so we'll get into exactly that, and I'll go through and derive electromagnetism. Here we go. All right, I'm going to quickly go over how to use some vectors and what the deal is. And again, this is a video, so if it's going too fast, you can pause it. If you think it's wrong, you can look it up, or write someone an angry letter. Not me, but write someone an angry letter, I guess. Because I probably won't read it, or I don't even really get mail or whatever, so whatever. All right. From quantum mechanics, this is, again, that state vector thing, and we can go through, take the derivative, and remember, just by the chain rule or whatever, this is going to be the partial, we can say it's the gradient, times this total velocity vector, which is this thing. So you can do the math, work it out, and see that that's the case, and we can do a little algebra, you know, put the vector here, blah, 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 and say, oh, well, we can just multiply, this is by 1. This is just the magnitude. I just chose to write it this form and this in the top, this form in the bottom. It's the same thing, you know, same thing. And then you can move that over there, move this h bar over on this side, and, you know, times a minus I times minus I is 1. So those cancel. That's why it's a minus I on this side. And then you can see, oh, cool. Well, since this is the dot product, I can cancel off one of those vectors that it's dotted with, and left with this. Okay, put the psi on the outside. So this is m velocity vector gamma equals minus I h bar gradient on psi. And this gradient is also, sometimes people write it in this form, kind of a tensor-ish form, d by dx mu, where this means x, y, and z, or x1, x2, x3, or if you include times the thing, x0, x1, x2, x3. So that would be the gradient. And so we see, well, this is a momentum vector. That's what that is. And we see, okay, well, if we take the momentum dotted with the radius, so we get the radial component, that's good old momentum that we found earlier. So that's just a way that you can do quantum mechanics, or put it in vectors and say quantum field theory, be fancy. But that's what it is. That's one thing you can use. So here's some vector stuff. This is just a way to put it in vectors, vector form. So this is like the radial vector. This is, again, in this case, the gradient also happens to be the unit radial vector. And that's just because the partial works out to this. And so you can check that. We did that before. This is, conservation of motion again, the basic law of physics I gave you. This is just another way to write it right here. And these are just some interesting, or some pretty much obvious things you should know. This is one way to write the cross product, is this thing. So we can use that. We're going to use that. We can put this in terms of alpha. And what we do here is just use a vector identity to convert with the dot product and say, oh, well, just multiply this by 1. This is just 1 out here. So doing that, we can do a nifty little thing and just put the r here, and that way we can cancel off an r, put the c squared over on this side as in the denominator. And if it's in the denominator, then we just use Maxwell's thing. And this is the epsilon and the mu, or the E and the M, or whatever, I don't know what to call it. The E naught, mu naught, electric constant, magnet constant. And so this is what we're going to use. And if you know any electromagnetism, you should be, I don't know, having a heart attack or something right now, seeing that this is what's going to happen. But no, this is obvious. This just from this is pretty simple, but we're going to use it in a little bit. All right. All right, so continuing with the vectors, again, we start from this. This is just the Pythagorean theorem in 3 dimensions. And we can say, well, okay, break it up into a vector. And so that this dotted with itself is going to give you back this. Okay, boom, there we go. We can say this is the del operator, or the, I don't know, nabla, or whatever you want to call it. I think I'm saying whatever in this videos a lot. Probably a lot of other things too. Whatever. This is the total velocity vector, or that should be d by dt. Whatever. This is supposed to be a t. So divergence is this thing dotted with something. And so for an example, we can take this dotted with this total velocity vector, which is going to work out to this. And so we can go, oh, well, commute, these operators commute, blah, blah. Whip that outside, put these inside. Well, partial of x with respect to x is 1, so this is going to be 3 in here. Time derivative of a constant is going to give you 0, so the divergence of this is 0. And we can also say in fluid dynamics this would be incompressible. We'll use that later. So that would be incompressible, meaning that the vector, if you're looking at a vector field, then you try and like shrink the point around it and say, well, are there lines diverging from this? That's what this is a measure of, this divergence. So it's just meaning that that you can't compress it or expand this fluid or whatever. So that really just means that we can think of space, empty space, as an incompressible fluid, which makes sense. I mean, how would you compress or like space if it's really empty and there's really nothing there, or really what we would call nothing? How would you compress it? So I don't know. That's a way to think about it. So maybe those people that were like, oh, luminiferous ether, maybe you could say they were right in a way, but not really. They didn't really know what they were doing, but it's just kind of funny that you could think of it in that way. And that's really is kind of what it is. Anyway, moving on, the curl is just this operator crossed with something, the cross product. So, for example, we can cross it with this thing, and you can work out the awful looking math, and it just works out to this, and so this gets differentiated, so it becomes minus 1 over r squared, blah, blah. And we can whip the minus sign in there, and it just flips this cross product, flips the two things. We get this cross this, and so we're going to use this. This is going to be a vector potential. And interestingly, this cross product, this thing that's going on in here, remember this was also in that alpha that we were using, and that alpha was dealing with charges. And so, fancy that, this has to do with charge, because it's a cross product, angular momentum, angular velocity, all that good stuff. And that's what's going on here. Also, when people get into supersymmetry really, there are a couple other motivations for it or whatever. Which is really unneeded once you have this conservation of motion that I gave you. What they're doing is they're using things called Grassmann numbers, which are anti-commuting numbers, which really all it is it's this in disguise, this cross product here. You could argue that it's more complicated than that, but if you want to work it out, you can see that this is really what's going on. This is the thing that's giving you that quote curvature, the thing that's giving you the term, because if you take the magnitude of this or whatever, it's going to give you the sine theta. Well, if you this one, you take the magnitude of this, will give you the sine, depending on how you define the sines or whatever. But this one would give you the regular sine. And that we just saw before was the charge. So what happens in supersymmetry is you're trying to deal with charges, and you're trying to put particles and antiparticles and try and unify particles in a better way, and you end up having to deal with stuff like this. And people don't know why, and they say, this Grassmann number, it looks like we need to have an extra dimension for it. And that's another reason why physicists usually talk about, maybe extra dimensions. And it's because of this. This is the culprit right here. And so this is anti-commuting. You switch the order, you switch the sign, and this is what is controlling. This is what's controlling that curvature, or really the omega, or if you saw it before, you saw the equation, so you should know what I'm talking about. Anyway, we can take the ordinary derivative, and it's just going to give us this, so we might use that. And again, just the magnitude of the total velocity vector is conserved. Conservation of motion. You can get everything from that. And, it can have whatever direction it is, so if you want to say it's minus c, then this would be in the opposite direction. But the magnitude, the length of it, is just this. So we can take the derivative of it, and, if it had a time component, if we wanted to define this with a time component for some reason, then it would be this, d by dt would be 1, and then this would work out like this. And so sometimes what you'll see something in this form. So partial time with respect to this. And this would be like a tensor derivative right here, because this would be this on a vector. So you're like, what's that? Well, that's what it would be. And often the Navier-Stokes equations are written using this, and so just to show you what that's all about. And we can also see, again, that the derivative of this is 0. Why? Because it's a constant. So it doesn't change. This is 0. So that means this whole thing in here is 0. And so if you wanted to, we'll get to the Navier-Stokes equation in a second, but it might make it almost too simple or trivial if you try and use this, but we can do it a few different ways. Anyway, moving on. All right, I'm just going to go through this real quick. There's a few more things, a few other ways you can put things in. You can pause the video and look at it if you want. But this is just to show you some other things you can write it in, like the gradient on the radial velocity vector. You can write it this way. You can write the total velocity vector this way. And also then you can go through and put momentum in this form with the charge. So a charge-momentum relation. And so that's another way you can do it. And so then you can use this way if you want to, put some fancy stuff in here, make it an operator, and so you can use that later. If you know how to do the math, then, I shouldn't have to tell you all this stuff. You should be able to do it yourself and go and fix Lagrangians left and right. So, all I'm not going to go through every single Lagrangian, by the way. I mean, there's uh, there's a Lagrangian for every day of the week, and well, every day of the year, and many years, and everything. I mean, you can make as many Lagrangians as you want. So there are tons of them in physics, and using the law or the relations I showed you before, you can go through and fix all of them and see what's going on. Anyway, this is a conversion factor. This is, again, what alpha is. It's the sine squared is 1 minus the cosine squared, which is this. And so we can just analyze this a little bit and say, well, all right, fix r, keep it constant, right, sum r. Then this alpha is going to shrink as the magnitude of the mass shrinks. So as the mass goes down, this alpha is going to go down. Fix the mass as as your distance goes down, then the alpha is also going to go down. And for any velocity, if you increase the velocity, then plus or minus because it's squared, as you increase this, then this alpha is going to go to 0. It's going to shrink and go to 0 eventually. So, and actually be 0 at if you're going at the speed of light. So for small mass and small orbital distance or radius or however you want to measure the distance to the thing, usually it's going to be an orbital distance, especially for if you're saying it's an electron orbiting a nucleus, well, and it's going to be at high speed, then this alpha is going to be really small. And so that's why you get that crazy numbers, 1 over about 137. So what was it? Wasn't it Feynman or something? Said, what do you say? Fine structure constant. All good theoretical physicists put it up on their walls and worry about it. It's like, well, I'm not a theoretical physicist, nor did I worry about this. I was just doing some math so I get my mind off problems and off my problems and just figured this out. And well, actually, I went and corrected. Like, oh, that metric for special relativity looks wrong. I'll just put this thing on the other side, and oh, okay. Well, this solves everything, and the fermions, bosons, all that stuff. So it all just I did it in like 20 seconds, but it was, yeah, I don't know. I'll talk about that later. But this is what's going on, and so we'll move on. Electricity. Well, first I want to just mention this. I forgot to do it last time. That, well, said at fixed m, at fixed mass, as then this quote coupling constant, this alpha, is going to go to 0 as the distance goes to 0. And this is what's called asymptotic freedom, and that's why they see that going on in quantum chromodynamics and the quote strong nuclear force. All it is the same force, gravity, magnetism, same thing. That's what's that's the same thing on all scales. It's kind of funny, but that's what they call asymptotic freedom. So we'll mention that again. Again, F equals ma, and this is what alpha is. This is the acceleration, and we can write force in these 3 different forms. Really, Triforce. There we go. I just wanted to write that. But these are 3 different ways you can write it. And, I mean, you can write it all sorts of different ways, too. But these are just 3 easy ones to do. And this is the one where you see an inverse square law. This is the one where you see it falls off with 1 over r. And this is a scalar type. So you would call this maybe a scalar field or a Higgs field or whatever you want to call it. It's just this. It's just force. And you're going to see this if you mess it up and you don't have the right things in your Lagrangian and whatnot. Then you're going to say, well, whoa, Higgs stuff. And we found this at exactly, they'll probably find it, whatever. Well, it's kind of like people in a dark room and there's an elephant, but they don't know it's an elephant. They're all feeling different parts of the animal, and they're like, oh, what's this? This is like a tree trunk. This must, they're like, oh, well, there's, 3 people have found one. We're going to predict a 4th pillar over here in this corner. And then someone goes and touches it. They're like, oh my gosh, there's a 4th pillar over here. And it's like, no, that's the elephant's 4th leg. And then someone's like, oh, it's a snake. It's like, no, that's the elephant's trunk. And so, so that's what's going on here. And so, I mean, it's really just this. But if you don't realize the underlying concepts and you don't actually have this in radial form and you put it in X, Y's, and Z's, then it really just obscures everything for you, and it's really hard to see what you're looking at. So it's just nice to take a step back and see what's going on. So this way we can break this up, use what the charge is, put it in here, and we see, oh, okay, well, this is force. This is really electromagnetic force, or it's the same force. But we can see clearly right here in this picture, this alpha, varies with, this is always between 0 and 1, so this is always going to be positive right here. This alpha is always going to be positive. So we can decompose it into all sorts of things, but this alpha is always going to be positive. And so, because we have the minus sign tagging along, we can put it with one of the charges. So one of the charges is going to be plus, the other charge is going to be minus. So if one of the charges is positive, one of the charges is negative, then we're going to have an attractive force. And that's why it looks like there's an attractive force if the charges are opposite. This is all that's going on. This is the mystery right here. This is it. So, and if you start from this and you just say, well, we'll just throw in a charge here and throw in another charge here, and they happen to be the same charge, well, then you're not going to have the overall minus sign out here, and so it's not going to be an attractive force. It'll be a repulsive force. But really, this is what's going on. If you decide to say, well, we'll call something charge and something, we'll call it plus or minus, whatever. Well, if they have opposite sign in here, then the overall force is going to be attractive. If they have matching sign, then the overall force here is going to be going to be repulsive. And so that's all that's going on. That's this mystery here. So this is really the gravity, magnetism, nuclear forces. It's all the same thing. It's all the same thing. And you can just write it in these different ways. And if you get confused and you don't really know what you're looking at, then you're going to think there are other forces, and you're going to have to put these arbitrary constants in front of it, and those constants are still going to change and run. And then you're going to have holes in your theory, and you're going to, you might be able to predict where your holes are, because you're like, well, there's supposed to be something there. It's like, yeah, because your equations are wrong, and so you can call it whatever you want, whatever type of particle you want. You can invent all sorts of names, and people have invented all sorts of names for things. They'll probably keep doing it too. People don't like change, and people like to be stubborn. So I am under no illusions that thinking that all of this stuff that I'm saying that anybody will like or listen or care. I'm under no illusions, believe you me. I fully expect people to stone me in the street, and it's like, how could you say this about forces and blah blah. Like, well, dude, just do the math yourself. I am fine to just give you guys this video and never look at physics again. I just figured this out and couldn't keep it to myself. So here you go. Anyway, let's move on. All right. Now, I guess I didn't mention this last time. This over here is called the vector potential, and this is called the scalar potential. And so this is a vector, and this is a scalar. And this happens to come in with a minus sign simply because normally when people are doing this, they're using the metric for special relativity or whatever. So what happens is the time component, the dt, will have a plus sign in front of it, and then the dx, dy, dz, those terms will have a minus sign in front of it. So then when you take the gradient, that'll have a minus sign. So this is just reflecting that. That's all that's going on with that. So, if you chose to do it the other way, the minus sign would switch. But this is just what's going on. And I think last board or whatever, I think I didn't write a gamma. It doesn't matter how you define it. I think I'm just going to use it this way, just because it makes things easier and consistent and whatnot. So I'll just define it this way and go with that. So this right down here, this is alpha again. Again, this is this unit vector, so its magnitude is 1. This one I figured out for you a little earlier, so we can use it. And this is Maxwell's thing right here. So from F equals ma
We can go through this whole nifty derivation and show again this was the curl. Did this before an example, and blah blah. Put this in here. Oh, fancy that! That's the vector potential. Curl the vector potential, and so this is what the force is. So we can whip this charge on the other side and call it a day. Call it magnetism. And so again, I put the gamma in here to make it consistent, and so that way it makes it a little easier if you try and you can now. I'm not going to go through it. You can go through it if you want to do it and derive Maxwell's equations. This is it. This is it. This is all that's going on. So this is magnetic. This is the electric. And you can see, oh, they're both force. Huh. How can that be? Bear's driving. How can that be? Well, magnetic field is this. Electric field is this. And we can put them together and see what happens in the next slide. So, and again, this is Q times gamma is this constant, and this is actually a constant now. It removes the time dependence, and so now it doesn't have any dependence on anything. It's just a constant, and that's the reason we can whip it inside and outside of this gradient, and there's the curl or whatever, and mess with it like that. So that's why. All right, next. So here are different ways to write the forces. Again, this was the electric field. And a field is just something with a value that varies in space. It's just with a vector. That's all it is. Nothing fancy. It sounds crazy, but it's like a field. That's all a field is. So it has this gamma in here. And so this is the electric field. This is the magnetic field. And we can put it together. Just call this r hat. And then we can put it in this form and just forget the gammas. I mean, you know where they are. And together, this is usually or sometimes called the Lorentz force or the total electromagnetic force, whatever. And you notice, hey, wait a second, that's twice the force. This is actually twice the force. Well, yeah. Yep, because it's the same thing. And especially if you don't recognize it and you try and do quantum mechanics and stuff, you're going to find different things, different quote anomalies like, oh my goodness, the electron has twice the magnetic dipole moment or whatever. And so you can figure stuff out just based on this. And so you can add another force to those sides or do it like this. Divide 3 by 3 and hey, look at that. Well, fancy that, sugar pants. We've got 1/3 here, 2/3 here. And you can manipulate this other ways to get minus in this case. And then you're going to see weird things happening with these out here. And also, since there's a charge hiding inside of these electric and magnetic fields, you could put more in here and do, by 1/9 and by 4/9. And if you wanted to go that way. But this is showing you, well, hey, this is why you're seeing, quote, quarks with 1/3 charge. If you try and break it down this way and try and say, well, they're interacting by this strong nuclear force, then you're going to get not only things that look like they have fractional charge, like this, but you're going to get things that look like you should have 3 generations of matter, like 3 different things of the same type with 3 different possibilities for the mass. And so you can work that out with this. F equals ma, there's 2 different ways to write this. We can say, well, let's throw and make this a field, throw a vector on it, unit vector on it, and say, okay, let's call this a scalar field or a strong field or whatever. And we can do the same thing with this one. Say, well, let's call this a weaker field. And then this one, same thing with gravity. You can throw this in here and say, let's call it a gravitational field. And again, this is what the G is. It's not a constant, it's this. And say, okay, fine. Well, again, this, just expanding this out so you can see this is 1/3 the charge, 1/3 the charge. And again, you can manipulate this more and do 1/9, and so you can put it 1/3 in front of this too. But again, this is the field. This is supposed to be the field. So if you're just going based off of, well, there's a given field, then what are these other things going to do in the presence of it? Then you'd have a 1/3 here and blah, blah. And so you'd have a 1/3 in front of here, and you'd say, okay, well, we've got different generations of that. And again, you can do 1/9 and go this route, and then in this case, with this m squared, it would have, the same thing, generations of matter.
So you can do it that way, and if you're an actual particle physicist, then you can take this and check and go through all your Lagrangians and have a blast. And I'm not going to hold your hand through this whole thing, but you can throw them all together in one expression, and here you go. So you've got 0 equals the gravitational field, the weak field, the strong field, this force, electricity, magnetism. There you go. I mean, this makes it look more complicated than it is, but it's just force. It's just force. That's all it is. And when you don't recognize what it really is, then it looks super mysterious and crazy and fanciful. And that's it. All right, let's move on. Okay, so just doing a little more now. This is, again, force. There are different ways to write it. You can also write it this way. It's the same thing. This is just a way to put a constant with respect to time times this alpha. So in case you're wondering, oh, well, how do you get a coupling constant out there? And, well, this is how. You can write it all sorts of ways. There's another way to write it like this. You just put one of the alphas and expand it out, and then put the other one as what it is. It's 1 over the gamma squared, and you can put this, the charge into the gamma, so we'll use that in a second. And again, this was what we used last time and said, okay, well, if we're going to use electromagnetism and call that a whole thing, the Lorentz force and whatnot, then we're going to run into using this, the 1/3, and that's going to be, times of mass and give us stuff like looking like we have generations of matter, like 3 different types of quarks and an electron, a muon, a tauon, or whatever ons you want to say. And they're going to look like they have the exact same properties and everything, just with different masses, and so this is the culprit. But anyway, this is one way to write it, so it's the same thing, just an identity. I mean, but then we can use it and plug in what these things are, and so, or multiply through by R, gamma, divided by Q. What this is this is a potential. Remember, this top is a potential, and then divided by a charge is, that's another type of potential for like electrical or magnetic or whatever. That's another way to make a potential. And for example, in quantum chromodynamics, which we're looking at right now, if this is going to be a representation of the strong force, because we can represent force by anything, we can plug in what these things are. So pull this one down and use it here, and then pull this one down and use it here. And again, it's got this 4/3 and minus blah, blah, blah in front of it. So expand this out, and again, write it down what it is, minus 4/3, this constant in here, and you can pretty this up a little bit. I just left it so that you can see exactly what everything is, and times the charge squared over R, plus this thing, which is a constant here, just has something with respect to the energy here. This is times regular R, so you can write it in this form here. And again, this is the potential, and well, lo and behold, that's the quantum chromodynamics potential. So it's got both these parts in here. If you know what you're doing and you know what I'm talking about, you'll recognize this and you're like, oh my goodness gracious, that's amazing. Yeah, that's what that is, and I'll use that in a second and expand on this. Well, not in a second, I'll do that. I'll do something else first and then get to the Lagrangian for this and whatnot. Anyway, again, conservation of motion. This is all you need. Do everything. And you can expand it out this way. There are tons of different ways to write all this stuff, by the way. I mean, you can write it however you want. Again, this is the curved V or curvy, whatever. Just another way to write it. And potential energy here is this or this. So we can flip this over here, and so it's going to be 0 equals this whole thing, and we can divide through by the volume, that meaning dividing through by R cubed, and that's the pressure, or minus the pressure here. And we get this other thing, and this is supposed to be a sigma. People usually write it sigma for some reason, but again, that's the pressure, and this is called stress. That's what this is. You can tell it's stress, like something being stressed, because if it's bending, this is again a curvature thing. Per volume, you have a certain amount of stress in this region. Then that's what this is, and so we're going to use that in a second. And it has the same units as pressure. So you can check that and make sure it's right and whatever, and throw rocks at me if you don't agree and whatever. But this is density, this rho thing, mass per volume. And this is what people call, for some reason, a body force. They just put a curly QF or something to try to make it look different. It's just the force divided by volume, or force per volume. They call it the body force. Fancy name. I'll only use it in a second. And this is just a relation between the density and acceleration, which the acceleration is the derivative of the velocity, or the radial velocity, really. So we'll use that in a second. So this is taking way too long. I'm fading and pretty tired, but well, I'm gonna finish it off. So this is almost done. Gonna hit the last stuff and just fly through it. So it's a video. You can pause, rewind, whatever. So you can deal with that. But I'm gonna start booking it. I'm going to go through this pretty quick. I'm getting tired. I want to finish this up. Anyway, this was the pressure, and this was the stress, and so I can work it out this way, and then just take the gradient of the whole thing, and this would be the zero vector, or whatever you want to call it. I'll just put 0. And so we can put this in another form, blah, blah, like this, and say, well, if we want to, we can actually width this out and make it look like a divergence. In that case, it's like a tensor derivative, and this would be like a tensor, and so with like a double hats in here, whatever. But that just works out to this, like a matrix. So this is a pretty simple tensor or whatever. But we can put it in this form, and I just put D for diagonal elements. So we'll use that in a second. But again, we found this out, divergence of this space. We can treat space as an incompressible fluid. So this is one thing that's taken as true, or for whatever, for the Navier-Stokes. Usually, well, not always, but for most intents and purposes, when people are asking about the problem, that's and do that. So we found that's true. Anyway, this is what it is. Remember, total velocity vector. And again, remember the time derivative of it is 0. So this, if you expand it out this way, the way it's usually written in Navier-Stokes, then it's going to be 0. So again, that's from conservation of motion. So it all makes this, if you plug this in, it makes everything almost trivial in this problem. But anyway, I mean, we should make things as easy as possible. I mean, if you're just making it hard, it usually means that you're not understanding the underlying concepts as well as you could. That's usually when things look complicated. So, I mean, not always. It is what it is. But anyway, that's that. Moving on, this is the density, this is acceleration. Again, the acceleration is just this. So we found, through this whole video and whatever, that this is really what the acceleration is about. You don't have any acceleration if you're moving along an arc path. So you just have acceleration when you're moving along the radial path. And so that's, again, force. Force is along the radial path. So we found all that. So so this is really the acceleration vector. It's the time derivative of this, if you want to call it an acceleration vector, then the total acceleration then would be 0. But this is really the acceleration we're looking at. So you can use either one and plug it into these equations, and then it's arbitrary. But this is what people call the body force, and so that's a vector. I just matched it up here. So, but this is the acceleration vector, this one, and then plus 0 to both sides. Just add this thing across, and then say, well, this is, put this in this divergence operator form with the tensor, and put this in here in terms of density, and expand this out. And if you like, then you say, well, I don't want to use this form of acceleration. I want to use the regular Navier-Stokes way it's written. Okay, fine. Put that in there. That's going to be 0. You're going to have to bring this term over onto the side, and then you absorb it into this. Because this is just the diagonal elements. But if you want to add more things in here arbitrarily, or heaven forbid, change this body force, arbitrary, whatever, change the initial conditions, arbitrary, whatever, just it absorbs, very easily absorbs right into here. And by all the equations that I gave you, you can see, mass, momentum, energy, all that stuff. You can you can see exactly what it is, and it would just go into these components here. So you could write it like this. This would be like the total stress tensor with shear forces and whatnot in there too. And if you didn't want to write it in this form, you could write it in this form, and it's do what you want. But the point is that this, you can do this for arbitrary stuff, for arbitrary parameters, arbitrary initial conditions, whatever you want to do. It's arbitrary, and it is a smooth solution because, again, we put everything in terms of sines and cosines, and those are infinitely differentiable. It's called smooth. I mean, you can differentiate until the cows come home, and that's what's going on. And so that's existence and smoothness or whatever. And the solutions solutions to this always exist. I mean, we went through and derived them from the beginning, so we know they exist, and we just wrote them in this form. It's really not. I mean, if you went just from the Navier-Stokes equations and tried to go backwards, sure, you'd run into plenty of problems, but we realized that this is what's going on. And especially when you try and pull the components out, the x, y, and z components, pull them apart separately, then we saw how you run into trouble trying to do that because it's sines and cosines, and sure, you can do it, but, it's going to make things a little more complicated, and we'll get into that more later, but anyway, this is what's going on in conservation of motion. This is the fundamental thing that I gave you, this tool that really is what's going on, and you can see that makes sense. Motion would be conserved because that's the thing people are always worried about in these Navier-Stokes equations, like, oh, are there infinities or there's singularities and blah, blah, blah. Like, no, dude, it's just this motion's conserved, and so, I mean, you could start at this point and derive this, or if you start at this point and say, well, we don't want infinities to come into play, then okay, you can derive this. But what's going on is this is really what's conserved, and so if you muck around with this, well, you're going to violate conservation of energy. If you're trying to measure it at a certain point or a certain distance out or a certain location, position, and you muck with this, then you're going to mess with the conservation of energy. So you can't do that, and then this would be, you can do perpetual motion or whatever, so that wouldn't work too well. But this way you can expand it out and say, well, what happens if it's not, or what happens if we try and shrink this? Well, if you just shrink it by a constant factor, then you just redefine what this constant is, the c, so that doesn't change anything. But if this epsilon does vary, well, the only useful thing you can do is put it into another component, a different component that's not this omega component or this radial component, because you can figure that out and just put it back into this and put it in, add another arbitrary force, add another whatever you want to do, and put it in this. And we, again, those are in terms of sines and cosines, so that's not a problem. But the only way it would be a problem is if it's in another component, in which case, if you're going to say it's less than this conserved quantity, that say Kellen motion is really not conserved, and you say it's slightly less, like, okay, fine. Well, it's going to have to be a new component, this vector, and guess what? That's going to have to be an imaginary component. So, good luck with that. And so that's not realistic. So that would have to say, like, no, you can't. You need the motion to be conserved. So that's the conserved quantity that it's hiding out, that people have been wondering about Navier-Stokes, like, oh, maybe we need to find a new conserved quantity, like some sort of mathematical entropy or whatnot. No, it's really just this, conservation of motion. That's all you need to do it. So there you go, Clay Peoples. I don't know, whatever. I doubt this meets the requirements of the problem, whatever, but there you go. So turbulence. Well, starting off from the equations I've given you, is you got this for distance conversion factor, and so you can whip that up over on that side and divide through by r cubed, the volume again, and we can get the density here. So we can work this out. And this, I mean, this is what alpha was again. I mean, we can write this in all sorts of different ways, so I guess that's what we're going to do. So here we go. We can write this like this, and I call this the magnetic factor just because I don't like writing all this stuff. But it also makes it more clear that this is having to do with magnetism. Or, I mean, you could equivalently say it has to do with electricity and put electric factor. But this particular one in this form is really the magnetic factor. And we'll see that in a second. But we can put it in this form. See, notice this r to the fourth over this density. So you can put it in this form. Remember that, oh, well, what was the alpha again? And so we can see it's again, this cross product, it's this this rotation basically is what's going on, and this is the curved part of the velocity. So that's that right there. We can put this in terms of that, just in terms of acceleration, and whip that in there, put that, what that is. And again, this acceleration is the derivative of velocity, so of the radial velocity really. So it's the rate of change of velocity. So I'll use that in a second. But this is, again, working it out, putting this over here and working out what it is. So we can group, if we want, we can group this like this and throw another curved V up top and put it within a distance and call it a cube. And then we're left with whatever's down below. So again, this is the curved V to match up because we want the same thing. So and lo and behold, this is the same units for kinematic viscosity. This is the other viscosity, this mu, not the magnetic constant or whatever. This is just a different mu. But this is supposed to be a nu, I guess. I don't know. Just all sorts of different letters. They'll all look the same. But this is supposed to be the kinematic viscosity related this way. And you can check the units. Let's make sure this is right. Yeah, that's right. And this is then the only thing that you're left over with is this, I guess Kolmogorov called it the energy dissipation rate or something like that. But I mean, you can see that it's basically like that because you've got a velocity. And if you think this is supposed to be something like, if you're supposed to have kinetic energy or something like 1/2 mv squared, and you take the derivative, then you're going to have, the 2 is going to come down and knock out the 1/2, and then you're going to get left with a v, and then the derivative of the v. So this is the form that you're getting, and then you have the minus sign for the energy to compensate. So that's what's going on with this energy dissipation rate thing. And so you can see it's a little funky, but that's the units are all work out and whatever. You can check that in the privacy of your own home. Anyway, this is Kolmogorov, the Russian dude from years ago. He was trying to figure out turbulence, and he did some like dimensional analysis on it and said, well, units, the only units you'd make out of it are like this, and it's like this. It's the same thing. Really, it's secretly this, this relation, all this stuff that I've showed you. It's this. That's all it is. He said, well, we'll come up with this fancy, characteristic length or whatever that's like this. And it's like, well, it's actually just a distance. This is all that's going on. And this viscosity term, all that is that's a representation of the curved velocity. And I mean, that's like conservation of motion. Remember, if you slow down in a radial direction, well, your motion has to go into an arc direction. And this is all that is. So the more viscous something is, then the more it's going to slow things down as you're trying to move radially. Then all that means is that motion is going to have to go into a rotational motion along a curved path. And so that's equivalent to saying that, well, a moving charge generates a magnetic field. That's the same thing that is going on here. And it's, again, by this whole thing. So work that out. I mean, if you have trouble, go back and watch it again. But I'm going to keep on booking through this. So this is what's going on. And so you can say, okay, how about Reynolds numbers, this crazy thing, that people are all confused about. Well, it's just this. You can put it in this form, blah, blah. Remember what this was? Kinematic viscosity down below. And what was that? Okay, it was this. And all right, bam, cancel the R's. We get this little ratio of the radial velocity to the curved velocity. And so, lo and behold, I mean, you can cancel the C's, put this cotangent, or you can square it and put it in terms of the alphas. And so now you can see, well, all right, let's do a little bit of looking at this. And as the magnitude of this Reynolds number goes up, then this alpha goes down and vice versa. And so, whoa, okay, what happens when the alpha goes to 0? It goes all the way down when this Reynolds number gets real high. Well, remember, that's when a theta is going to be 0, because sine theta is 0. So that's what's going to happen there. And remember, we explored that, and that was a phase transition. We did all that good stuff and showed how that's related to, chaotic things and entropy and different things like that, and fractal patterns and patterns in general. I mean, remember from that sequence I showed you, the logistic map that is really behind the phase transition, uncertainty principle, whatnot. that it actually has a repeating pattern when you have when the initial angle, when the s over h bar or whatever is a rational number times pi. So there are times, there are angles that this goes through where you get a repeating pattern, and that is what happens when you get things like pattern generation or spontaneous pattern formation and different things. And no classical dynamics or no classical whatever is going to predict that, but this does. I mean, because this is showing you what's really going on. So this is saying, well, look, yeah, the patterns can form and they can disappear and they can look self-similar at all distance scales, and then you get fractals, and that's related right here to this. So you can see, I mean, people for a while were like, well, turbulence is somehow related to this, and what's going on? I mean, you look at a plume of smoke, and it kind of goes into fractal-looking patterns and different things like that. This is what's going on right here. So there you go, guys. Let's move on. So this is quantum chromodynamics, or Yang-Mills theory, or non-abelian gauge theory, or non-commutative gauge theory, or whatever you want to call it. But I'm going to go through some example here. So this is, I'm not sure if you can see this if the glare is bad, but whatever, I guess you can deal with it. I'll explain it. This is the energy again. This is this. You can put it in this form. This is the Lagrangian. You can put it in this form. And so with a little manipulation, you can put it over into this form. Yay, there we go. And then divide through by 4, and so you can get it in this form if because people are probably going to expect that they're going to be using this 1/2 mv squared. So anyway, and again, this constant in front of the Lagrangian, you can multiply it or divide it by whatever you want, constant factor. It's not going to change your equations of motion. So anyway, this is what that invariant distance was, the distance in terms of energy, whatever. This is just the invariant charge, or the charge constant. There's no, it doesn't even depend on energy. It doesn't depend on anything. It's just a constant. So this is a true constant. Anyway, going up here, F equals ma, we can write it this way. That's minus e squared over h bar c times alpha, and, well, just square it. And so we can get this. And we can do some little algebra and whatnot on it, and put the charges over here, because remember what we did with electromagnetism? We said, well, it's, we're going to make an electromagnetic field or an electric field or a magnetic field, and so you divide that by the charge. So that's what we're doing here. We're going to have an extra one out here, though, an extra charge squared, so we're going to use that and see where that comes in. But anyway, we can mess around with this a little bit, put it in this form. There you go. And say, oh, well, let's call this some certain field, some sort of gauge field. And well, I mean, it's undefined right now. I mean, it's just saying, like, well, it's a field, so it's like force per charge and times some. We don't even have to say that it's necessarily in the radial direction. We can just say it's in whatever direction, this gauge direction. So I mean, this is completely arbitrary. We're just putting it in terms of force, and that's it. I mean, so that we can do whatever we want with it now. I mean, and this is just that factor, just grouped it into one thing. So that's what this is, and so this is, again, this thing right here was the force squared, so we can just, manipulate with that. And so all this is this. I mean, you can put this in a tensor form like this, and all this is the scalar. I mean, this is the the field strength. That's what this is, this square. So that's all this is. I mean, and it just makes it so that you can make it whatever you want as long as it agrees with whatever else, which you can do that. I mean, it's real. You can, for an arbitrary thing, I mean, you can do this. And so again, this was, well, I just wrote this here. This was mass, so we can use this and see, oh, remember, it can be represented in terms of charge. So we'll use that in a second. Anyway, this is what the Lagrangian now becomes, and so you can plug that in there. And now going up here, you can divide through by that k and put that over here. And so now you can rewrite this a little bit, and this part is just an actual pure constant. This q is just constant. So we have this over r cubed, so now we can have a Lagrange density, and woohoo. And I mean, you can manipulate the chart. If you say, well, there's gammas in there, well, you can throw them over here and say, well, this, this field has carries charge with it, and like a gluon field or whatever you want to call So you can manipulate that to your heart's content, but it's really not. It really doesn't change anything. So you can have a Lagrange density, which is what people usually use, and anyway, going down here, this is the same thing. So we can whip this over here, make that a density, and take this thing, call it a factor, call it a number. It's just a constant, so we have the same thing. It agrees up here, whatever. Pull out what the V was, extract it, put it in this form. We can do that. It's perfectly fine. And so get this. And again, in front of the Lagrangian, it's just a constant factor, so it doesn't change the equations of motion. You can do whatever you want with that. And so anyway, we come to this part, and so boom, there you go. Minus 1/4 and Q. And I mean, again, you can do different numerical manipulations to change these and whatnot. But again, this is just completely arbitrary. It's just it's completely open to what you want to do with it. And you get these terms over here. So you can say, okay, well, these are the other terms. And, well, you can make, I mean, this G is here. This field strength is right there. So that means that you can take any G that you fancy, you know. If you want to be Mr. Fancy Pants, then you can put this into a gauge covariant form, and with a potential, a certain gauge potential or whatever, A, with the gauge, you know, constants here or whatever, and those will, whatever you want to determine. So this works for an arbitrary thing, and as long as you make sure that the gauge potential that you are left over with this, which you obviously are. I mean, this is something that's here. This is something right here. As long as you have this, then you can use it for any arbitrary gauge field. So there you go. And again, this is well, we saw way before when I did the running of the coupling constants, the running of the bulls in the China shop, which actually they, according to a TV show, the bulls in the China shop are actually not very destructive. Anyway, this mass is related to the charge. So this means if you say, well, okay, well, gluons are supposed to carry charge. Okay, bam, there you go. Got a mass gap for the glue balls, or whatever you want to call them. I mean, secretly, if you're actually taking everything into account, all the forces and whatnot, then something that has zero charge, or has zero mass, then has zero charge. But if you're throwing multiple things in here, and you're going to say that gluons have a charge, and then you're going to, split up the alphas and all that, then you're going to get this, and that's what would be a mass gap. So, again, asymptotic freedom. We went over that with the alpha coupling constant, and as distance goes to zero or whatnot, the alpha is going to go to zero. So anyway, that's what's going on, and so you can work with this, and it looks more complicated than it has to be. It's just that, and that's the typical thing for all these different Lagrangians. I mean, you can do all sorts of different things, put them in all sorts of different forms, and if you don't like something I did in here, then just do a little bit different manipulation, and there you go. It's like, it's really, there's all sorts of things you can do with this. So now you can, run free through the flower fields and, have fun with your Lagrangians. So anyway, let's move on. Almost done. A few more boards and that's it. I'm so ready to be done with this. You have no idea. I'm sure you are too. But anyway, just to go over a few things, I want to make sure if I missed or whatever. Again, defining the magnetic field in terms of a vector potential, a curl of a vector potential. Well, if we do that, then the divergence of that is going to be zero. So that means no magnetic monopoles. Sorry, guys. I mean, you could argue and say that you're going to define this a different way and blah, 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 and, with the gamma and say that that's going to affect something. And, well, I mean, you can do whatever you want. I'm not going to stop you. But this way, the way that we went through it, we're not going to have magnetic monopoles. And that just makes sense because of what charge is, of what we're saying charge is. And charge is that rotation, that omega. That's really what it's a measure of, that the sign of theta, and that's in terms of the r and the omega. So if you want to do the magnetic field, which is, the perpendicular thing, and see that that's quantized, well, then you're going to have some problems going with that. So that's not going to work out. The only reason that you would do magnetic monopoles and things like that would be like, well, like in string theory, you'd use that or whatever. But, I mean, we already found that, well, I mean, they were kind of on the right track with string theory, looking at that mass squared thingamajigger, or what's it, of the force, that representation of the force. And so looking at that, they recognized, well, there's something going on there. So then with they tried to play the renormalization game, and where you come into the Riemann zeta function, and the only way to get that to work was to is like the sum over infinity is like minus a 12th. It works out somehow mathematically or whatever. So like, well, that means you have to have 24 dimensions and or 28 or whatever it is. It depends on what you're doing. It really depends on how many dimensions you need. So anyhow, that's what's going on. That's why they were kind of on the right track with string theory, saying like, well, it's maybe vibrating strings or whatever, and going on. It's actually just space. That's all it is. I mean, well, we can call something space or call it nothing or call it something. I mean, we went over that. It's pretty much arbitrary, but it's really just a curvature of your path, or curvature of your orbit, things like that. And so that's what's going on. And yeah. So anyway, from the Lagrangian last time, you might see that this is similar. Yeah, it's kind of similar. This is what the approximation is for superfluids at low energy, I think. And in here, again, like at low energy at low omega, then the sign will become it'll become close to just x, just the function y equals x or whatever it is. So this can be a good approximation in here. So that's why you get something like that going on. And again, you can play with the Lagrangians and go through and see and do stuff with and things and what have you. Anyway, so and this, but again, the phase transitions and stuff, we went over that, and that the phase transitions are things for everything. I mean, it's like from what we would say nothing to something, from out of the empty vacuum to liquids and solids to sonoluminescence, the bubble collapsing down, and then when its velocity hits zero, and we did that, whatever. You can examine that. Well, then it's going to it's going to change direction, so it's going to emit the photon and blah blah. It's just because it's doing it so quickly that you're going to get a higher wavelength, then you're going to emit light, or you might interpret that as saying, well, another way to say it is, well, it becomes a plasma. Like, okay, cool, you can do that, and you can calculate the temperature. The actually correct way to calculate temperature and whatnot, I showed you with thermodynamics. So anyway, that's that. This is another conversion formula. I don't know if you see it. You're like, oh my goodness, that's so amazing. Just MVC equals PR omega, PRW, whatever. This momentum, velocity, speed of light, or mass, velocity, speed of light, momentum, distance, angular velocity. So that's all together. But anyway, moving on. You can look at the potential energy or the force, one way to write the force, and this was a way to write the potential energy. And remember, this was what string theorists were like, oh my gosh, there's something going on here. And this is another thing where if your stuff's off, then you're going to have a scalar field, and you're going to say, well, Higgs bosons, Higgs fields, and I don't even know what a Higg is, but I guess it's a dude that, like an old dude that was talking about spontaneous symmetry breaking or something like that. But anyway, this is all that's going on. I mean, I hate to rain on anybody's parade that like about the Higgs stuff and the dark matter, and it's like well, if again, it's like the elephant in the room that nobody knows is there. It's a dark room, and they're all thinking it's a bunch of different animals. It's the same animal, It's like I don't mean to like minimize anybody's discovery of whatever if they discover it, but it's like, well, can you, it's like a black hole. Can you well, you know something's going on. You're seeing the effect of something, but it's just your interpretation of what that something is. The cause is off, and it's like, can you take a Higgs boson and put it in your hand? You know, like give me a bottle of Higgs bosons? No, like then all it is light. So I mean, I guess you could bottle light or something. If you a mirror glass, you could say it's bottled. I don't know. I'm not going to argue philosophizing. Anyway, this is a way to write the potential. And remember, last slide, whatever you want to call it, with the Yang Mills business, this was in there, and so boom, boom, we can write in this form, and okay, there we go. That's a potential that grows with distance, and so say, well, potential that grows with distance means confinement. So it means like, well, if you to separate them more and more, it's going to require infinite amounts of energy, and so that's all that's saying. And I mean, you can put other terms in there or adjust for other terms. So depending on what you want to put as the gauge potential, depending on what you want to put as the gauge potential, then you can mess with this all to your heart's content. But I mean, we realize that if we're actually dealing with regular force and we're not going through the whole non-abelian gauge theory and all that stuff, and we're looking at the actual like realistic physics and whatnot, and then, well, obviously there's no thing about confinement really, because things transition all the time. I mean, but stability and mass and different things like a proton or a nucleus, or is going to has a much smaller radius. So and it doesn't have much radial velocity, much outward velocity. So like if you're looking at it, it's not moving very very far. Whereas the electron, it's much lighter, so it's going to have less mass. So then it can have a larger orbit. So that's why it will orbit around a nucleus, and so on and so forth. So and that's why we see different things going on with the nuclear physics and stability, and that's why things become more radioactive when you get bigger. I guess I can do that in the previous slide or something like that. But anyway, that's what's going on with this, and so you can do this, and if I mean, look, I'm not a mathematician or physicist, or I'm not anybody. So I mean, like, give me a break. I don't want to argue with people on the internet about stuff. I mean, unless I can sit down with somebody, with you, or you can sit down with me, and I can show you I can walk you through the math and exactly everything, or you can try and walk me through and show me exactly where I'm wrong, and like, okay, cool, but I'm, like arguing on the internet, it's like, no, it's not really the greatest. Anyway, moving on. The way to represent time, again, was this. So we found, it's got this inverse cosine thing going on. That's kind of crazy. But for tau, the proper time, the time that the target would experience, this is the time according to the observer, this is the time according to the target, or the observed thing, then it's going to be this, which is a little nicer. This has this. And so, again, when you try and work with space-time, you're going to get a lot of grief trying to deal with this. And again, with renormalization comes into this, and we'll see how this connects to Riemann zeta function, which is connected to the distribution of prime numbers, which really all the prime numbers is like, if a number's prime, it's just saying, well, according to multiplication, like, you can't express it in terms of other things. So that's just a consequence of what's going on with, for example, with trig functions. They're transcendental functions. I mean, then you can't represent them certain ways. It's like pi. You can't represent that by a rational number. It's like there's nothing really mysterious about it. I mean, you know that it's the ratio of the circumference of a circle to the diameter, but if you're trying to put it in other things like square or rectangular coordinates, then it's like trying to fit a square peg in a round hole, and it's like, well, it's a different thing. You can't exactly represent it correctly that way. And that's the same thing that's going on with the prime numbers, and that's why this math is connected. And so it's like, well, the prime numbers, you can't represent them as factors of smaller things, just one in itself. Like, well, that's why. That's another way to look at it. And again, that was we saw that in that chaos where that sequence with the entropy, with that sequence was by and large not periodic or didn't have a pattern, but it did have a pattern sometimes, and that's why we actually see spontaneous patterns and different things like that, sand piles and whatnot. That's what's going on with that. But anyways, this is the mathematical heart of it, and this is something that also shows up in things like renormalization because you're trying to deal with this mess. So anyway, this is that zeta function. I don't know. And this is not the spin or the entropy number. This is a different thing. This is new here. Put this down. So this expression up here is only valid for when the real part is greater than 1, I think. So otherwise it's divergent. So and that's S is a complex number. So Riemann came up with this functional form. So put it in terms of itself. And the gamma function, this is just factorial in disguise, and sine and this pi business. And so this is valid for all the complex values except for the singular point or whatever at 1. So then the trivial zeros are supposed to be, the so-called trivial zeros are at s equals these things. So you can see that when this sign is 0, then it's going to be with these. If you say, well, wait, you're missing out on some other s's. And like, well, actually, it's because this gamma function will have, I'll show you how this is represented in terms of gamma functions and whatnot. But what happens is the gamma functions as a pole, so then that, like an infinity basically, so like a 0 and then divided by 0. So as you take the limit, whatever, they will cancel out. So those aren't valid zeros for this function. So the only ones are these here. So anyways, that's that. We'll explore that in a second. And the quote non-trivial zeros are when the real part of S is between 0 and 1. People have narrowed it down to. But the hypothesis, the original Riemann hypothesis, was that all the zeros are only when the real part of S equals 1/2. And so we can do that. I'm going to go through this thing and prove it for you. I'll really derive this, so yeah. I don't know. Let's do it. I'm going to go get a drink first and pause this and come back. So here we go. This was that functional form that Riemann had put it in. And so we can transform this into the so-called symmetric form where it's symmetric. And I'm going to write it this way, because we're going to use this later, but that way this gamma's down here, this pi's down here, and we're going to use this, and this is part of it. And this is how the gammas are related, the gamma functions. Again, the gamma function's just a factorial in disguise, and I'm not going to write down what it is, you should know. But again, this is a video, you can pause, rewind, look up stuff on the internet, and well, I'll probably disable comments on the video. I mean, I'd rather just talk to people in person than, argue on the internet. But anyway, this is what the gamma function is. So we have this conversion that we can do and whatever. Anyway, well, suppose that this zeta function is 0 if the real part of S is 1/2. Okay. Well, not only if, but if this is 1/2, then this has a chance to be 0. I guess I should phrase it, but you know what I mean. Well, cosine inverse of 0 is 1/2 pi. I mean, saw that earlier, and this was going on with the spin and whatnot, but that was in there. Cosine inverse, there you go. It's right here. This is where it comes into it. So should be pretty obvious if there's something where a real part, especially a real part in complex numbers, usually have to do with a cosine. And if that's 1/2, then it's like, well, something's 1/2 and a 0. Well, it's this relation right here. So we can throw the pi on the other side and say, okay, well, that would be this then should be the real part of S if we're going to mess with it. Say, okay, well, for some number A, it goes in here. then we're going to look for if the real part of s is 1/2, and this a is going to be 0 or whatever. That's going to be the relation here. So we can whip this pi on the other side, put the cosine. And again, the real part of s is just 1/2 times the thing plus its complex conjugate, because the complex conjugate, makes the imaginary part minus, so that cancels. Then you get twice the real part, so you need to divide by 1/2, and that's what this is. So write that here. Throw the pi on this side, and there we go. Whip the cosine over, and here we go. So call this theta. Call this part theta. And so we can put it in terms of like a unit complex number, or a psi. Like we use it for a steep function, or whatever, steep vector. But just use it this way. And then we're going to look at building the Riemann zeta function out of this. So, I mean, it's going to be something times this. I mean, this is you're going to have a magnitude and then this. So this is part of it. Anyway, again, this is the psi, and this is in terms of this. So I'm going. All right. I think last board or whatever, I had written an extra 1/2 down here, which shouldn't be there, but I'm not even going to worry about it. I'm writing it here now, so that should be obvious to you anyway. So should have been obvious to me, I guess. But anyway, going on. This is what we said psi was, and so we can say this is theta pi times the real part, and so that way we can say, well, when the real part of s is 1/2, then the real part of this psi is going to be 0. Okay, cool. We did that. This cosine would be 0. So, okay, fine. We can use that. So up here, this is what theta as a function of, because theta is a function of s, this complex number s. So we can put this in, expand out what the real part of s is. It's, 1/2 times this plus this. So it's just this. We can expand that out and say, okay, well, now, what if we do the 1 minus s, that reflection thing, this symmetric looking thing? Well, 1 minus s, we can work it out. The complex conjugate of 1 minus s is just complex conjugate of 1, doesn't do anything, so it's just the complex conjugate of that, and we see, well, it's this right here, pi minus the original theta. And so, well, plug that in, use trigonometry, and the trig identity. Always remember it, sick cats positively can't sing, and then it's just A, B, or whatever the first, this and then this. So this is 0, sine of pi is 0, cancels this, cosine of pi is -1, and then this, the minus sign go in or outside of the sign, because it's the type of function it is. So then it just becomes this, sine of theta times 1 minus s is this, so we get this symmetric type of thing. And we can do the same thing with a cosine and say, okay, what about the 1 minus s part? And well, throw that in there. And this one, I always remember by Crazy Cats Never Sing Softly. An old teacher did. Old teacher went through these mnemonic devices and they stuck. That's funny. But anyway, the cosine of pi is -1. There we go. Sine of pi is 0, so we just get this. You say, oh, that's too bad, it's not a symmetric function. Okay, square it. There you go. It's squared, and now it's a symmetric function. So now we can build stuff out of these. We build stuff and multiply them together. We don't want to, we wouldn't really want to add these because of, because we want it to be 0, either from this part or from this part. We want either one to be able to make it 0, because as we noticed, this sign was in the Riemann function, the zeta function, whatever, and this has to do with this, similar to the gamma, so we'll do that in a second. And so we want this to be in there somewhere, and this one we want that to be in there somewhere, because we know the Riemann zeta function has at least tons of zeros all over the place when this real part of s is 1/2. So we know it's got to have something that makes it, that makes it able to have a 0 there. So this is in there, and you're like, well, it's going to work at all those places. And I'm like, well, it is. So we'll look at it in just a second. We'll continue on.
All right, continuing on. And by the way, this is this is by no means mathematically rigorous or anything like that. I mean, if you're a mathematician, go check it and throw rocks at me later. Well, I'll check it later. But I wanted to finish this video and just get the physics out there. This is, and people are always wondering about the zeta function renormalizability and that sort of stuff. And so I'm just trying to show you that, well, you know, it's in terms of trig functions, and these gammas are these gamma functions, these factorials are in terms of trig functions. And so it's kind of like if you do it the other way, you're trying to put a square peg into a round hole, and so you're going to have problems with it. So anyway, oh, there should be an I here, an extra I, whatever. You get it. This is again the real part of S is this. This is, we can throw it into an angle, throw it into a unit length 1 complex number, and do it this way. Pull it out. Use some identities. This is a way to hit it with an exponent, get it in this other form. And so you can see, well, okay, if you get a valid solution to the functional equation, well, then you can raise it to a power as long as you're not flipping it, as long as it's not negative power something, then you can multiply through by a power, and so the zeros aren't going to change. So that's just a tool you can use, and then this is to show a reflection relation, and then pull it apart like this, and again there should be a little extra I here, because broke this apart. And anyway, this is showing, well, this is, you can pull this apart into these components, but it's not going to satisfy a reflection relation, like you can't put this on this side, so without doing some other crazy stuff. So we'll have to use, some trig functions for that. So anyway, this is identity for the gammas, and you can do some little algebra manipulations and put it in this form, this form. And again, you pull out the 1 here, and it becomes an S. And so you see, well, this, we're going to have to put things in terms of these gammas, if because usually these gammas have poles, meaning they go to infinity, so they'll be on the other side in the denominator, and those will be zeros. So those are possible zeros depending on how you want to build a function out of these things. So, and again, you could say, well, it's like a Fourier transform or whatever, but yes, but it's a little more restrictive because of these and what's going on here, and for example, this. So it's like saying, well, you want to build these gammas out of here? Okay, well, again, they're going to have to satisfy that functional relation that we saw just before. So we'll get to that in a second. And this is a way to pull them apart. And so you can see, well, if you are so inclined, you can put out expressions for the imaginary part also. And so, like if it's an imaginary part and it still has an I in here, then if you take the sine of that, then that's going to be a sinh or hyperbolic sine function. And so that way you can divide by it, and you'll only get a pole at one value, so you can shift that. And it's up to you. But anyway, it's cosine, and you can pull out the gammas with this nifty tool. And again, this is just the product of the different gammas of the different stuff. Actually, I think this should be a gamma. Anyway, look it up. I'm getting tired. But you can, then this is just rewriting what we did on the past slide or something, I guess. I think I wrote it on there. But you're going to use this and plug it into the sines and cosines. And this is another thing that we can use that's, well, it's not exactly or symmetric or reflexive or whatever the term is. It has the minus, but we're going to make use of that minus, so we'll see that in a second. All right, moving on. All right, so again, this was the angle that we used, and this is the real part of S, for pi times the real part of S. This was this little nifty partially reflexive thing that we're going to use because what we can do now is, again, this you can plug into here and see that it's reflexive. It satisfies this relation here. This one doesn't by itself, neither does this one, but if you multiply them together, it sure does. And you can use this and build stuff out of it. And so again, we can do the same thing using this phi and pi times the imaginary part, and then you can check that it's got this relation. So then you can throw that into trig functions and use it and build more stuff out of that. So you can build stuff out of the real parts of S and the imaginary parts of S. And you can use this, and again, this is a function of S, so
that's going to factor into that. And you saw how we built other stuff out of that and could build the gammas out of them and whatnot. So the mathematician take it and use it and whatever. So this is a way to use the sign, and we can the sine 2 theta. So again, you can use powers or multiples of the angle and everything inside here, but you need to account for whether it's going to actually satisfy this relation. And so you use this. You can use powers of this or whatever you want to do. You know, appropriate powers to conserve the sign or save the sign or eliminate the sign or whatever you want to do with it. But again, that's, you know, work with the gammas and make sure, and if you have the gammas match up and everything, then you're good. And then you can convert with the gammas this way again. So this is it. So anyway, this is that relation, and so one thing that satisfies that is this with the zeta function. So we can say, well, we don't know what this is yet, but well, we can take this and say, well, that's 1. So does this work? No, because this at 0, because this is going to be a pole, would be 0. But we know that this one right here is at 0 is minus a half. Pretty obvious. So fancy that, Captain Fancy Pants. You can now use this. Use the fact that the imaginary, you can use a hyperbolic sine function since at 0 is 0. So you can, what you can do is you can cancel off this pole right here, this 0. So, you know, provided that you're taking the limit and all that jazz and whatnot, then you're going to get, you can throw this in here and, you know, or have this times this whole combination. But then you can also have this k function, have this cosine, and so this whole thing will be, will satisfy this relation, and so, and plus the combinations that satisfy it, and you can multiply this over and through and whatnot, and make sure that you keep track of the gammas. And so right here we showed an example, because this will go to 0, and this will make this whole thing 0 here, and so again we can put parentheses there. But and so you choose. We already did this for the minus a half, and so I'm not going to work it out for you, but you can do that by yourself and work it out to get the minus a 12th. You use a gamma function, which you use a gamma function, you know, in a factorial, and you get the factorial to match up with this k, and this k at minus 1 will give you like minus 3 halves, and then you use minus 18th or 1 over 18, and blah blah blah. You can do the math if you want, but these are some tools, and this is to show you that yeah, you can build this zeta function up in terms of this other stuff, and lo and behold, well, it's gonna, you know, you're going to have to do it in terms of imaginary parts and real parts, and when the cosine is 0, when this whole thing is 0, well, that's only going to happen when this real part of s is 1/2. So, I mean, or you could say minus a half, and then, but you could take absolute value, square it, and do the appropriate manipulations. But this is what you're going to get. So you have to build it out of stuff that satisfies this relation, and so the only stuff that does is going to give you the appropriate zeros. So that's that, and just review and let you go in. So finally, it's over. I hope you're as glad as I am. But if you actually watched, thanks for watching. I mean, or just skipping to the end. But and I'm sure there are errors. Yes, I will probably go over this and very soon discover many. But the concepts are what you need to understand, and what well, you don't need to. I mean, it's not going to save your life one day probably, but it might be useful because it solves a lot of problems in physics. And just this right here, this is it. This is really all it is. And I mean, yeah, I'm not a physicist or whatever. I just was messing around with some math. Had nothing else to do, you know, computer or whatever, and just like, well, this metric for special relativity looks wrong. Like, well, I'll just put that part on that side, and oh, okay, get this. And so I went through and did a bunch of stuff, and it was just the past. Wasn't very long ago. It was like a month. So, and then I've just been trying to go through and fix different things in physics. So, yeah. Be gentle with me on the reviews. No, just kidding. Things are supposed to be scrutinized heavily, and so please do. And I will too, and I'll probably find out there are a lot of errors. But anyway, take it, run with it, and I don't know, go do what you want, have fun. And oh, by the way, I'm not just a floating stick, but I'm a real person. Hi there. Anyway, yeah. Like my awesome whiteboard there, I got it out of the junk pile like a couple days ago. So it's hanging in there, but I think it's not doing too well. It's all bent up and everything. So, anywho, all right, peoples. See ya.